In this video, we're going to break down one of the most powerful ideas behind modern AI systems, that is, Retrieval Augmented Generation or RAG. We'll start from the ground up. First, we'll understand why RAG is needed, what problems it actually solves, and how it fundamentally different from simply prompting an LLM. Then, step by step, we'll build a basic RAG pipeline, from document loading and chunking to embeddings, vector stores, retrieval, and response generation. As the series progresses, we won't stop at a static RAG system. We'll upgrade it by adding memory so the system can remember past interactions, maintain context, and behave more like a real conversational assistant. We'll also introduce conversation threads, showing how multi-turn conversations are handled internally and how retrieval changes when history comes into play. Every concept will be explained clearly with practical examples and real implementation details, not just theory. And by the end of this video, you won't just understand how RAG works. You'll be confident enough to design and implement your own RAG pipeline from scratch and extend it for real-world use cases. So, let's get started and build intelligent retrieval-powered systems one step at a time. Most of the time, the data we want our AI system to use doesn't live in a single prompt. It lives in files, it lives in folders, it lives in PDFs, documents, spreadsheets, websites, and entire directories full of unstructured text. That is where traditional prompting starts to fall apart. You can't simply copy-paste a 200-page PDF into a prompt. You can't feed a directory full of policy documents into the chat model. And you definitely can't expect an AI model to answer domain-specific questions without having access to actual source material. This gap, the gap between real-world data and LLM processing, is exactly what gives rise to Retrieval Augmented Generation or RAG. RAG allows your system to pull knowledge from external data sources before generating an answer. But before you can retrieve anything, before you can chunk text, before you can embed text or build a vector store, you need to get the data into LangChain in the first place. And that is where document loader comes in. So document loaders are the entry point into every RAG pipeline. They take raw data, whether it's a text file, a PDF, an entire folder of documents, a CSV spreadsheet, or even a web page, and load it into a clean, structured format that LangChain can process. Without document loaders, there is no data ingestion. Without ingestion, there is no chunking. And without chunking, there is no embeddings. And without embeddings, RAG is impossible. So in this episode, we are going to explore some of the most commonly used document loaders in LangChain. The first will be text loader, which is perfect for raw TXT files. The next will be PyPDF loader, which is one of the most widely used loaders for extracting clean text from PDFs. The third will be directory loader, which will be used for loading entire folders full of mixed document at once. The fourth will be web-based loader, which will be used for scraping and loading content directly from web pages. And the final one will be CSV loader, which will be used for converting structured CSV rows into queryable documents. And by the end of this video, you'll understand exactly how to ingest almost any type of data, and more importantly, how these loaders become the foundation for everything we're going to build next. Because starting from this episode, we officially begin our journey into Retrieval Augmented Generation or RAG, which is the engine behind chatbot, knowledge assistant, AI search systems, and intelligent applications that rely on your custom data. So let's dive in and start bringing real-world documents into our LangChain workflows. Alright, so now that we understand why document loaders are such a critical piece of RAG puzzle, let's begin with the simplest and most beginner-friendly one, the text loader. Think of text loader as the hello world of document ingestion. If you have a raw TXT file sitting on your computer, maybe notes, logs, transcripts, script documents, anything, text loader's job is to open that file, read it, and convert the entire thing into structured LangChain documents. But here's the key. It doesn't just read the text. It packages the contents and its metadata in a format that every other LangChain component understands. That means when you later split this text into chunks, embed it, or store it in a vector database, everything flows smoothly because the loader already organized it properly. And this is important because TXT files are one of the most common formats you'll encounter in early stages of RAG development. When you're prototyping an idea, testing extraction strategies, or simply working with small datasets, you probably start with a small text file. It's quick, it's lightweight, and it helps you iterate fast. With text loader, even something as simple as a TXT file becomes instantly usable by your AI system. Instead of copying and pasting the content into prompts, which becomes messy, unscalable, and error prone, the loader brings it into the LangChain as a clean document object ready to move through your pipeline. And the beauty of text loader, like I said, is its simplicity. There's no heavy parsing, no special formatting issues, no PDF quirks, no web page markup, just clean, predictable ingestion. And because of that, it's the perfect first step in understanding how all other loaders work. So, what you're going to see next is exactly how we take a basic TXT file and load it into LangChain as a document. And once you see how effortless that is, you'll start noticing how every other loader follows this same pattern, just with different data source. So, let's load our first document and get things rolling. So for the implementation part, we're going to import document loaders from LangChain community, and inside that we'll have a loader here. So for now, I'm only going to import this particular content here. So basically, I have a text file named cricket.txt, but it actually contains a document here. It is a story about an LLM that I generated using Gemini model. So basically, I'm going to load this txt content into LangChain here. So for that, I'm going to call on loader and then call the loader class here. Basically, I'm going to provide my file name. My file name is cricket.txt, and then I'm going to use the encoding. If in case I have some characters that cannot be read properly. Okay, now if I do docs equals to loader.load, then I can see docs. I can see the type of docs. Then I can see docs 0. Okay, we'll see this and then we'll move further. So run this. So Python 6 document loaders, 1 text loader.py. So as you can see, whenever we printed docs, it has printed the entire content. Actually, the content is quite detailed here. So here, if we see the type of docs is a list. And then if we do docs 0, then it shows me the page content of the docs here. So what else can I do? Okay, I can also, let me comment down all of this. Then I can use docs 0. We've already seen the page content. We can also see the metadata of the document using this line here. So let me clear this output and then run the code again. So the metadata that the file contains is a simple source or file name called cricket.txt. And then if I want to see the page content of this, I simply need to do docs0 dot page content, and then it will provide me. It should provide me the entire txt file content that I have. Okay, so this is how we use the simplest form of document loaders, which is text loader. Now that we've warmed up with a simple text file, let's move to something a bit more realistic and far more common in real-world applications, which is PDFs. So PDFs are everywhere. Whether you're dealing with research papers, books, scanned documents, reports, manuals, college notes, or corporate documents, almost everything is packaged as a PDF. And unlike text files, PDF are not friendly. They have pages, layers, embedded formats, headers, footers, and sometimes even weird spacing or invisible characters. This is where PyPDF Loader becomes a lifesaver. PyPDF Loader doesn't just rip all the text out of the PDF in one giant blob. It loads the PDF page by page, meaning each page becomes a separate document object. And why is that useful? Because page level granularity gives you more control. Later, when you chunk, embed, or retrieve sections, the model knows exactly which page a piece of information came from. If you're building a RAG system where citations or references matter, this becomes incredibly valuable. Another powerful benefit is metadata. PyPDF Loader automatically attaches metadata like page numbers and file names. So if your RAG assistant needs to say something like this answer comes from page 12 of the curriculum, that information is available right out of the box. What's even better is that PyPDF Loader handles a lot of PDF quirks gracefully. Whether the document has tables, bullet points, or multi-column layouts, it tries its best to extract clean, usable text, so you spend less time fixing formats and more time building your pipeline. So in the demonstration, we'll be loading a PDF file, inspect one of its document entries, and then look at the metadata attached to it. So this will give you a clear picture of how PDFs are transformed into structured LangChain documents and how ready they are for later steps of splitting, embedding, and retrieval. Let's jump in and see how PyPDF Loader helps us to unlock the content inside a PDF. So here in this implementation, I have this PDF, basically an audit report of National Audit Office, or like of some form of organization. We'll try to extract the text from this PDF using PyPDF Loader. So for that, I'm going to import LangChain community.document loaders import PyPDF Loader. Then basically, I'll call loader PyPDF Loader, and then pass in the file name, which is audit report.pdf, and hit docs equals to loader.load. Then I can easily print the docs as well as the individual page of the docs here. So let me do print docs and then run this file. Okay, so one of the package is still required. So let me go to requirements.txt and then install PyPDF here. So I'll install the requirement -r requirements.txt. Let me install the PyPDF library first. And then rerun the code again. So as you can see, the first page document is loaded and then it is present inside page content. This page should also contain some form of metadata here. So to load the metadata portion only, what I can do is I can hit docs0.metadata, and then we'll be able to see what kind of information we have in the metadata section. So basically the producer of this PDF is Acrobat something software here. The creator is this, the creation date. We also have when the PDF was created. And then we have a title for this. We also have a file name. The total number of pages are 24, and then we are on page 0 and the page label is 1. So these are the additional informations that we have in the PDF metadata. And then if you closely look here, we use the same approach as we did earlier using this particular loader while loading a file here. The only Difference that we've done is we have used a PyPDF class in this particular case, and then the loading mechanism is the same. So this is how we can import our PDF files into our LangChain ecosystem. All right, now that we've handled individual files, both text and PDF, let's scale things up a bit. In real-world RAG projects, you rarely work with just one document. More often, you have entire folder full of files, multiple PDFs, books, chapters, notes, reports, manuals, or datasets scattered across a directory. Loading them one by one is not only time-consuming, it's also error-prone, messy, and completely unscalable. And that is exactly where Directory Loader shines. Directory Loader acts like a smart crawler for your local file system. You point it to a folder, tell it what kind of files you care about, and specify which loader should process those files, and it takes care of the rest. It walks through the directory, finds every title that matches your pattern, and automatically feeds each one into the right loader. The beauty of this is flexibility. For example, if your loader has 20 PDFs, you don't have to write 20 different load commands. Just give the directory loader a glob like PDF, attach the PyPDF loader, and every PDF in that folder becomes part of your pipeline with almost no effort. But here's the cool part. Directory Loader also supports lazy loading. Instead of loading all documents into memory at once, which can be a nightmare if you're working with hundreds of large files, it loads them one by one, only when you actually need them. This makes it incredibly memory efficient, especially for large-scale RAG systems or production environments. In the walkthrough, you'll see we'll load all PDF documents stored inside a folder, and instead of printing the content, we'll inspect the metadata of each document. And this will give us a clear sense of how Directory Loader organizes and streams document without overwhelming our system. So if your AI assistant needs to ingest entire libraries, batches of reports, or bulk research material, Directory Loader is the tool that makes that workflow not just possible, but clean, scalable, and efficient. So let's dive in and see how it handles an entire directory of documents. So for this demonstration, I have a folder called docs, and inside that I have 3 different PDF files. Now, to load the document of all these PDF at once or from inside this folder, I'm going to use Directory Loader. So from LangChain _community dot document loaders import Directory Loader, and then I'll also use a PyPDF loader. So I can directly call my Directory Loader class and create its object using passing a path first. So the path is the folder location that we need to give. Let me give out docs here. Then a globe, meaning this will represent what kind of files do you want to read from inside the folder. So here it can be any file with extension .pdf, which means all of these 3 files will be read from inside or by this directory loader. And then finally, I'll need to provide the loader class, which is going to be the PyPDF loader. Okay, so as we did earlier, where we are going to do docs equals to loader.load, and then basically I can print out the length of docs here, and also see the metadata of our document or loaded document. So let me clear this and then run this code. So since we have 3 different documents, it is not going to take so much time because these are small documents here. But when we are processing a large number of documents inside a text, then it can be somewhat slow. Anyways, the metadata here contains producer key, creator key, creation date, author, mod date, title, source, total pages, page, and yeah, things like that. But as I told you, there's also a feature of lazy loading our document here. So for that, let me comment it out, and then I'm going to do docs equals to loader dot lazy load. Now for documents in docs, I do not need to load all the data at once. Once one data or one PDF file is loaded, then it is going to show my metadata or show the files metadata in the output here. So let me rerun this again. So yeah, there are a lot of pages in this particular document, and then it did not at once produce the result, but it did it slowly, loading the document one by one, and then basically loading the pages one by one here. So this is how we implement directory loader in LangChain ecosystem. Now that we've explored loaders that work with local files like text, PDF, and even whole directories, it's time to step outside our machine and walk into the wild, unpredictable, and glorious jungle called the internet. And honestly, this is where things get really interesting. Because in real world RAG systems, your data isn't always neatly stored on your laptop. Sometimes it lives on a web page, sometimes it's inside a blog, sometimes in an online review, a product page, or a government site that refuses to format anything properly. And without a proper loader, trying to extract structured content from a live web page feels like trying to drink water from a fire hose. Messy, chaotic, and guaranteed to cause pain. And this is where web-based loader steps in like a digital superhero. With web-based loader, you can point to any URL and it jumps in, pulls out the readable text, cleans it, structures it, and hands it back to us like, here you go. Would you like this in a list of documents? And the best part is that we can instantly plug that loaded data into any of our LLM pipelines. So in this episode, or in this video now, to make things realistic, we will actually fetch a real web page and show you how easy it is to extract content from it. And to make it even more fun, we'll turn this raw web page into a tiny question and answer engine. We'll take the article text, feed it into a prompt, connect it to our model, and boom, ask the system a direct question about the web page content. No manual copy pasting, no scrolling, no headache. Just a clean loader that is invoked with a clean chain, and we get a clean answer. So this is the true power of document loaders. They're not just utilities, they are the foundation of a robust, scalable, real-world ready RAG workflow. And web-based loader in particular opens the door for endless possibilities. Product comparison bots, news summarizers, Nepali market research tools, travel information assistants, you name it. So let me now show you how effortless it is to fetch a live web page, load it, and immediately ask meaningful questions from the extracted text. So let's jump in. So here I'm first going to start with my import. So from LangChain community dot document loaders, we import web-based loader. Then from LangChain grok, we import chat grok. From .env, we import load.env. From LangChain core .output parsers, we import str output parser. Then from LangChain core .prompts, we import prompt template. And yeah, so as I said, we are going to turn this into a Q&A engine. So hence I'm importing all the models, the prompt template, and then the output parsers. So first of all, load the credential from .env file. I'm going to define my model. My model will come from chat grok. I'm going to use llama model. .3. Okay. Now I'm going to define a prompt here. So the prompt is going to be from prompt template. First of all, I'll write down the template for this one. So the template will be answer the following question. I'll keep my question inside a placeholder. question from the following text, and then I'm going to keep text inside another placeholder. Now everything will be wrapped inside our input variables, all the placeholders especially. So question will be one and then text will be the other. Okay, so let me go for the URL. So the URL I'm going to use is this one. Okay, first of all, let me make sure that the page is live. Otherwise, we'll get an error here. So, yeah, so the page seems to be live. So let me just paste down the URL. You can use any other URL of your choice, especially if that URL is kind of an article. So now I'm going to use or define loader object using web-based loader class, and then I'll pass in the URL, and then I'll do loader.load just as I did earlier. Now I'll define the parser using str output parser, and then I'm going to invoke a chain. So the chain will first take in a prompt. It will be passed to the model and then to the parser here. Now I'm going to invoke the chain. So result equal to chain dot invoke. I need to pass in the question here. So the question is going to be, what is the article talking about? Okay, let me see, what is the product the article is talking about? And then I also need to pass in the text. So for text, what I'm going to do is I'm going to do docs 0.page content, because I think it will contain the header that we want, and then from the header my model can answer the question here. So basically this is about car price in our country. So I should get the appropriate answer based on my question here. So now I'm going to print out the result. So print result, and then let me run this now. So clear everything in the terminal. So Python document loaders, and then for web-based loader.py. Okay, so it might need some package. Okay, so let's go to requirements.txt. I think it needs Beautiful Soup 4. So let me just install BS4 inside this. And then I'm going to do pip install BS4 directly, not from the requirements, because it will be done automatically from the requirements if I run it. But anyways, let me clear this and then rerun the code again. So it will try to scrape the content from the page and then try to answer here. So the product being discussed in the article is the Dongfeng Nami Vigo, an electric SUV launched in Nepal. So this is our answer. So this is how we can use web-based loader and basically scrape content from any website or any readable website, and then basically build a. Now that we've played with web pages and see how LangChain can transform online content into structured query-ready data, let's shift gears and move into a format that almost every real-world project eventually deals with, and that is CSV files. And honestly, CSVs are everywhere. Whether it's marketing data, survey results, user activity logs, bank transactions, product catalogs, education dataset, or government report, if someone hasn't figured out a fancy format yet, chances are it's a CSV. But here's the funny part. Even though CSV files feel simple, working with them in RAG pipelines is not always straightforward. You can't just give raw rows to an LLM and expect it to magically understand the context, the columns, the meanings, and the relationship. And that is where the CSV loader comes in, with a surprisingly elegant solution. CSV loader doesn't treat the dataset as a one giant blob. It goes row by row and converts each row into separate document object. This means each row becomes its own little knowledge packet, a self-contained chunk of information that the LLM can reason about individually. And this opens up endless possibilities. You can build a recommendation system from your product CSV, a customer segmented chatbot, a resume filtering agent, a dataset exploration assistant, and even a data auditing tool that checks for anomalies row by row. All powered by LLMs and all starting from something as simple as a CSV. So in this part, I'll load a simple CSV using a CSV file loader and show you how magically it transforms each row into a document object. This will give us full flexibility to process, chunk, search, map, or feed each row independently into an LLM chain. So let's take this very common and very practical file format and turn it into something intelligent, structured, and ready for any RAG workflow. So let's dive into CSV loader. So here I've first considered a CSV file called ads.csv, and then it contains a row user ID, gender, age, estimated salary, and so on. So this is my CSV file that I'm going to import here in CSV loader using my CSV loader from document loader class in LangChain community. So from LangChain underscore community dot document loaders import CSV loader. Now I can just call loader equal to CSV loader and then provide in the file path. So file path is going to be ads.csv, which is my file. And then here I'm going to do loader.load, just like I did in the earlier videos. So one document object for each row here. So let me just print data 0 first and then see what happens or what kind of result we get here. So Python, what is it? So 6 document loaders. Let me do this again. So Python 6 document loaders and then 5 CSV loader.py. So as you can see, our very first row is being loaded here. So the page content is user ID, and let me verify this here. So the page content is user ID, gender is male, age is 19, and then the estimated salary is 190,000. And then in case of the metadata, we have a source which contains a file name and then the row number from where this page content is being generated. So this is how we can load a simple CSV file in the LangChain ecosystem using the CSV loader class. And that wraps up our exploration of the most essential document loaders in LangChain. We saw how different formats like plain text, PDFs, folders full of documents, live web pages, and even structured CSV files can all be transformed into clean, consistent document object ready for intelligent processing. These loaders might look simple on the surface, but they're actually the backbone of a very powerful RAG system. Because without properly loaded, structured, and well-organized data, even the biggest LLM will struggle to give accurate, grounded answers. What we're doing in these episodes is actually building the foundation piece by piece. So each loader, each concept, each mini project, they're all stepping stones towards a complete end-to-end retrieval augmented generated pipeline. So in the next video, we continue moving forward and dive into text splitters, which is another crucial building block of RAG, where we'll see how to break large documents into meaningful LLM-friendly chunks. So stick around, because everything we're learning is leading us to a moment where we assemble the entire RAG system and make it work beautifully in the real world. Now that we've learned how to pull information from text files, PDFs, directories, web pages, and structured datasets, you might be thinking, great, I have the data, but it's huge. Now what do I do with it? And that right there is the exact moment why every RAG developer discovers their next big challenge. And that LLMs cannot handle your entire document at once. Your book is too long, your PDFs are too dense, and your scraped web page is full of mixed content. And your CSV rows are too large to process as a single block. So before we can retrieve analyze, or generate anything intelligent, we need to break the data down into smart, meaningful, and manageable pieces. And that's where text splitters are the unsung heroes of every successful RAG system. Think of them as the editors of your pipeline. They decide where a paragraph should end, how much context belongs together, and what size of information the model should see at a time. They prevent your LLM from choking on massive documents and ensure your retrieval accuracy stays sharp and relevant. In this video, we're going to explore how splitting works, why size matters, and how different splitting strategies suit different real-world needs. For example, sometimes you want a very simple fixed size slicing of your text. Clean, predictable chunks for straightforward tasks. Other times, you need something smarter, something that can look at your text structure and then choose the best breaking points, like respecting headings, paragraphs, or punctuation. And then there are the scenarios where code enters into the picture. Code isn't like regular prose. It needs indentation, functions, classes, and logic to stay intact. Splitting it blindly can actually remove its meaning. So we'll explore how to split code safely and intelligently. And finally, we'll look at a modern AI-driven approach where chunks are formed based on the meaning of the text, not just its shape. This ensures that related ideas stays together and unrelated content doesn't accidentally gets bundled into the same chunk. So these different styles of splitting gives you complete control depending on the scenario. Maybe long articles, research paper, scrapped web pages, multi-label structured documents, data sets, and even complex coding scripts. By the end of this episode, you'll understand why chunking is one of the most important steps in building a high-performance RAG, and how different strategies protect the context quality and how they affect the accuracy of retrieval later in the pipeline. And this is where your data truly becomes LLM ready. So let's dive into the world of text splitters and prepare your documents for the intelligence layer that's coming up next. So now that we understand why text splitting is essential, let's begin with the simplest and most straightforward form of splitting, which is the character-based text splitter. This splitter doesn't try to be any smart. It doesn't analyze structure. It doesn't look at headings, paragraphs, or meaning. Instead, it follows a very direct rule. Take the text and chop it into blocks of fixed character length. Think of it like slicing a long rope into equal pieces with a ruler. Cut every 100 characters, cut every 500 characters, or cut every 1000 characters, and so on. You decide the size. The splitter will follow it blindly. But why is this useful? Because sometimes simplicity wins. If you're dealing with extremely unstructured text like raw logs, old scanned documents, transcripts, or OCR outputs, there's often no reliable formatting or paragraph structure to respect. In those cases, a character level splitter is predictable, consistent, and surprisingly effective. You also get full control over two factors. The first is the chunk size, meaning how big each piece should be. Smaller chunks will be easier to process but more retrieval calls later. And larger chunks will be more context richness but heavier for the model. And the next is the chunk overlap. How much each chunk should remember from the previous one. Overlap is useful when you don't want meaning to be accidentally cut in the middle. But if you are working with very clean slices or very short chunks, you can keep it at 0. And what are the trade-offs here? Character-based splitting doesn't understand semantics. So if the text suddenly breaks mid-paragraph or mid-sentence, it doesn't care. Its job is not to preserve meaning, just to break things consistently. But for a lot of projects, especially in early RAG prototypes or fast experiments, this type of splitting is more than enough. It gives you a clean set of manageable chunks to feed into embeddings and retrieval. And then in our demo, we'll see how we load a PDF, slice it into fixed size character blocks, and print one of those chunks. Nothing fancy, just simple mechanical text cutting. And because of that simplicity, it is one of the fastest and most widely used splitters when you don't need structural awareness. Okay, so we'll start with something very simple. So from LangChain _text splitters, we're going to import character text splitter. And from LangChain community dot document loaders, we'll import a PyPDF loader. So now we will have one of our PDF file and then read it using PyPDF loader. So I'm going to read this audit report.pdf file that I have in my project folder. Now I'm going to load this first. So docs equals to loader.load. Okay, so once we load our document, I'm going to define my splitter object using character text splitter class. And then here I need to provide two variables. The first is chunk size, and then I can mention the chunk size as the length of the characters I need in one chunk. So let me give it 500, and then I will also provide a chunk overlap. The chunk overlap can be used as maybe 50 characters. 50, okay. And then let me define a separator. So a separator can be an empty space here. Okay, so in case of result, let me split my text using splitter.split documents. Since we have loaded our PDF in the form of document here, so we use split documents here, and then we use text. Now basically we are going to not print the whole result, but we're going to print the just one part of the result and then see its page content, and also we can print its metadata. So now let me run this. So Python 7.textsplitters and then 1.characterTextSplitter.py. Okay, so I might have missed something. Yes, I have missed a comma here. So let me do this again. And then save it and then run this code again. And I can see that, okay, it is taking some time to run. So let's wait. I think the PDF file is too long. That is why it is taking some time. So yeah, I've split, or like the page content is being printed here, which contains around 500 characters, like I said, and then it also can, and then I can also easily extract its metadata here. So this is from page 0, but the page label here is 1. Basically, it is the second part of our splitted text here. So this is how simple it is to use a character text splitter. Similarly, I can also split my text contents easily using this character text splitter here. So suppose if I have any text like Python text like anything, so this is a LangChain tutorial, so you are going to learn a lot in this series. So if we have this text, we can also use the same splitter, but the function will be quite different here. So the function that we are going to do here is splitter dot split underscore text, and then I need to pass in the text here. So this will also work if we have a string text in our project, or if we have a document, we can do the same using split documents too. So let me comment this out, and then you can try this on your own later on. Now that we've seen the simplest form of text splitting, let's move one step ahead into something far more thoughtful and adaptable. That is the recursive character text splitter. If the basic character text splitter is like cutting a rope into equal pieces using a ruler, then the recursive version is like having a skilled editor do the cutting for you. Instead of slicing blindly at fixed character intervals, the splitter tries to preserve natural language structure as much as possible. It works through a hierarchy of separators, almost like a checklist. First, can we split by paragraphs? If not, can we split by double new lines? If not, can we split by sentences? If not, can we split by commas? And only when nothing else works, break by characters. It keeps doing this hierarchy recursively, always choosing the best possible cut that keeps the text coherent while still meeting your chunk size requirement. And why do we need this? Because when you're building RAG apps, semantics matter. Your chunks want, or you want your chunks to feel natural. You want ideas to stay together, and you don't want a paragraph about space exploration sliced in the middle of a sentence or a bullet point chopped completely out of context. Recursive splitting solves this beautifully. It allows the model to receive chunks that feel more human and more meaningful, which drastically improves both embedding quality and retrieval accuracy. What actually happens under the hood? So imagine you give the splitter 200 characters as the limit. It first tries, can I keep whole paragraph under 200 characters? If they fit, then great. If not, it drills down. Can I split at new lines? If the text is still too long, it drills. Sentences? Still too long? Words? And still too long? Alright, now it's time to cut at characters. This small fallback approach is what gives it the name recursive. It recursively tries the next best splitting rule until a chunk fits your defined constraint. So what does this mean for you? It means your chunks maintains context, keep sentences intact, feel more natural, work better at or for embeddings, and improve your RAG pipeline's retrieval performance. So in the demonstration that we're going to do, we will provide a short sample paragraph about any topic, something with clear sentence structure and flow. Then the recursive splitter will intelligently break it into pieces that preserve meaning without forcing random acts. It's like having a text splitter that actually respects the writing instead of slicing it like a robot. And with this, we move from a mechanical cutting to structure-aware splitting, bringing us closer to the world of truly optimized RAG processing. So first of all, we are going to import recursive character text splitters. So that will come from LangChain _text _splitters, import recursive character text splitter. Then I don't think I need a PDF loader here. So anyways, I'm going to import some text and then this particular text will be chunked using the recursive character text splitter. Okay, here is the text. I've just copy pasted it in case it'll be easier for you to read it. So I'm going to do word wrap. So this is a small text content which is about space exploration here. So now I'm going to define my splitter object, and then that will be defined using recursive character text splitter. Then you provide the chunk size. So let's provide the chunk size of 200, and then let's do chunk overlap of maybe 100 or maybe do 10. So if this is it, then I am going to split using splitter dot, since this is not a document, this is only a text, so I can use split _ text function and then pass in my text here. So let me print out the result and then see if it actually preserves the meaning before it tries to split it. So first of all, activate the virtual environment. So my venv scripts and then activate and then run this. So Python 7.text splitter and then 2.recursive character text splitter. Okay, so if I run this, then I should see my result. So my result contains two different splits here, or multiple splits in fact. So the first split that I can see begins from here to this particular full stop here. So the entire sentence meaning is captured here, meaning it's not breaking out in the middle of the sentence in between words. Similarly, here if we see, it did try to preserve the semantic meaning, but it had to break it down in between of the sentences, because it could because the next sentence was too long, and then it tried breaking it down. Maybe it tried doing it on the comma, but the length of the context was too short. So yeah, it broke down in the middle, and because I have a chunk overlap of 10, the word medical is being preserved from the previous context to the next context, or the previous chunk to the next chunk. So this is how we implement recursive character text splitter. Similarly, if you have a document You can simply load your document using PyPDF loader or like any other type of loaders that we've talked about in the previous video, and then basically use split underscore document function to split your document content. So just like splitting the text, what we can also do is we can also split codes. LangChain ecosystem also support the split of code. But whenever we're splitting a code, we need to preserve some form of semantic meaning in the code. The code might contain class, functions, or statements, maybe conditions, loops, etc. So whenever we are trying to break down our code into different chunks or our code content into chunks, we want to make sure that the semantic meaning of the code is also preserved, meaning the chunk is not broken down in the middle of a statement, or it is not broken down in the middle of a class declaration or a function declaration, or in between a condition. So now we'll see how LangChain ecosystem supports that exact breakage of context into chunks whenever the content is in code, and then we'll take an example of Python code here. So for this implementation, we're first going to import recursive character text splitter. So for that, let's import it using LangChain text splitters. Import recursive character text splitter. We'll do it using two ways. So let's also import Python code text splitter and then a language here. So now let me copy a block of Python code and then paste it here, and you can pause the video and then see what is pasted here. So we have a Python class called student. It contains an init function with name as age and grade as its parameter. Then we have get details method and then is passing method here. Then we create a student1 object, and then we basically print out the details or basically call the get details function. And also we have implemented an if else condition to check if the student is passing or not. Now to split this particular code here, what we're going to do at first is use the splitter using recursive character text splitter, and then here we're going to call the recursive character text splitter dot from language. I think okay, so I think this is already deprecated. So here what we're going to do is we're directly going to do Python code text splitter. Then we'll define a chunk size. So the chunk size will be 300. The chunk overlap here will be 100. And then let me split my text here. So splitter dot split underscore text. Again this is a text content, so we'll use the split text function. If this was from a Python file or someplace else, we would use split docs here. So we'll pass in the text, and then basically we will print our chunks here. So let me see, or we'll see our chunks here. So yeah, use this text splitters and then 3.python text splitter. So if we see the chunks here, then the first chunk begins from here to the end of our init function. I think wait, so this is inside our is passing function. Is passing function is passing, is this is passing? Yeah, so we have our first chunk until here from the top, and then the next chunk is from the is passing function again, because we have done some chunk overlap. So the next chunk goes from here down to the end of our code. So in this way, the semantic meaning of the function or the Python code is preserved. The chunk is not broken down in the middle of the statement, or without including maybe the function declaration and the function statement here. So this was possible using recursive character text splitter in the old library, but now it seems to have been removed. during the new update. So along with Python code text splitter, you can also find some other, I think you'll also see some other type of text splitters here. So HTML section splitter, JS. For JS we have JS, then I think we should have something for NLTK2, then Spacey2, and then stuffs like that. So yeah, this is how we can split our code, not only text but also code using the splitter function from LangChain text splitter module. And with that, we wrap up one of the most important building blocks of any retrieval augmented generation workflows, which are text splitters. We started by understanding why splitting matters, how unstructured documents can overwhelm an LLM, how large chunks reduce accuracy, and how tiny chunks breaks context. Then we went hands-on with different splitting strategies. We began with a simple size chunking approach. We moved into the more intelligent and adaptive recursive character text splitter, which gives us fine-grained control without manually defining every rule. And then we even explored how the recursive splitter can adapt to code, respecting its structure and logical boundaries. So all of these tools gives us the power to recognize messy, unstructured content into rich, meaningful, model-friendly chunks. So this is a stage where our raw documents begin transforming into something an AI system can understand and reason over. And now that our documents are cleanly chunked, structured, and ready, the next step is to give them a vector meaning. So in the next episode, we move into one of the most crucial concepts in all of RAG, which is embeddings. We'll learn how text turn into numbers, how similarity search work, and how embeddings power the intelligence behind the entire retrieval system. So get ready, because this is where we start stepping into the real magic of RAG. Now that we know what we are sending into our retrieval system, it's time to understand how the system actually understands those chunks. And today, we move into one of the most crucial components of any RAG pipeline, which are embeddings. So embeddings are how we turn raw text into mathematical representations. Those are dense vectors that capture meaning, relationships, context, and even subtle nuances between words or sentences. In a traditional keyword search, the system looks for literal word matches, but with embeddings, the system looks for semantic similarity. It understands that the two words doctor and physician are related, even if the exact words never appear. This is what makes your retrieval intelligent, adaptive, and capable of handling natural language queries gracefully. We'll talk about why embeddings are absolutely essential in modern RAG pipelines. First, they allow your system to perform semantic search, not keyword matching. They let you compare and retrieve related ideas even when phrased differently. They enable vector databases to rank responses by meaning, and they form the foundation of context injection for LLMs. After we understand the concept clearly, we'll jump into hands-on demonstration. You'll see how to generate embeddings from your text chunks, store them, and prepare them for vector search. And by the end of this video, you'll be fully equipped to move from text processing to true semantic understanding. So let's get started. But before we dive into embedding models and their implementations, let's start with a bigger idea that makes all of this possible. That is, the vector space representations. In natural language, words are abstract. They carry meaning, relationship, intent, and context. Things that a machine cannot understand directly. But if we convert words into vectors, numerical points in a multidimensional space, something magical happens. Words that are similar in meaning end up close to each other, and words that differ in meaning naturally drift apart. So this is the essence of vector space representation in NLP. We take language, something humans understand intuitively, and map it into geometry, something computers understand perfectly. And this is meaningful because now we can measure similarity not by matching letters or keywords, but by measuring the distance between 2 points in space. This is why classic examples like king minus man plus women is equivalent to king, and even the doctor is equivalent to the word physician. The geometry captures semantics. But instead of manually designing these vectors, which is impossible at scale, we use embedding models. These models convert text into fixed size vectors that preserve meaning, context, relationship, and even the tone. And we can do this not just for words, but for sentences, paragraphs, and entire documents. Now, if we connect this to RAG, and when we ask a question inside a Retrieval Augmented Generation system, the LLM doesn't search for keywords. It converts the question into an embedding, places it in the same vector space as your document chunks, and finds the closest vector that is the most semantically relevant piece of information. You can think of RAG as the scaled version of finding similar words in the vector space as shown here. But instead of comparing single words, we're comparing the entire chunks of knowledge. Instead of searching one dictionary, we are searching thousands or millions of vectorized text space. And this is why embeddings are absolutely foundational in RAG. They identify how your chunks are represented, they identify what gets retrieved, and they determine how accurate your final answer will be. So in this video, we're going to explore this concept hands-on. After understanding the intuition, now we'll generate real embeddings using a Hugging Face embedding model and use them the way RAG systems do to find meaningful, semantically similar document chunks in the upcoming videos. So let's begin the implementation part. So here, for this implementation, I've already created an API key from Hugging Face Hub and then pasted it into my .env file. Now, let's import LangChain underscore Hugging Face. Sorry, Hugging Face, LangChain underscore Hugging Face, import Hugging Face embeddings. So not sure why this is being too slow, but anyways, the import is correct. And from .env, import load underscore .env. Import load underscore .env. So let me load the credential first, and then I'm going to define my embedding model here. So my embedding model is going to come from Hugging Face embeddings, and the model name will be sentence transformers all mini lm l6 v2. So this will be my model for today, and here the text that I'm going to convert it into a embedding vector will be this one. So New York is a busy city with a lot of population. So this is a text that I have here. Now what I'm going to do is I'm going to do embeddings dot embed query, embed query, and then simply pass in the above content here. Now if I print out the result and let me run this. So to run this, let's first of all I'm going to activate my virtual environment. And once that is done, I'm going to do Python. Okay, what is the folder name? So 8, sorry, not here. Python 8 embeddings and then 1 Hugging Face embeddings.py. So if I run this, I should see a list of numerical values here. It might take some time because the model might need to be downloaded and then downloaded locally, and then maybe it needs to be run, or I think it will not download the model. Instead, it is going to access the model through the Hugging Face API key directly here. So let the embeddings be loaded and then I'll show you. Okay, so as you can see, I can see a collection of numbers here. and then this is the embedding vector for this particular content here. So if we had some documents here, then we would use the embed docs function instead of embed query functions here. So this is going to be absolutely essential in our upcoming videos, where we are going to implement the RAG based systems here. So this is all for the implementation. And that brings us to the end of our deep dive into embeddings. So we explored how vector space representations give meaning to language, how embeddings convert text into meaningful vectors, and why this entire process is the backbone of any retrieval augmented generation system. Whether you're dealing with short phrases, large documents, or entire knowledge bases, embeddings are the bridge that allows LLM to understand, retrieve, and reason over your data. So in this demo, we saw how easily we can generate embeddings using Hugging Face models, and how these vectors open the door to semantic search, relevance scoring, and intelligent retrieval. So in the next video, we're going to take this a step further. Once we generate the embeddings like you see here, we need a powerful way to store, index, and search them efficiently, and that's where vector store comes in. So we'll explore what they are and why they matter, and how to use them to make retrieval blazing fast and scalable. Now that we know how to generate embeddings, the next big question is, where do we store these embeddings? And even more importantly, how do we search through them efficiently when our dataset grow from a few lines to hundreds of pages or even millions of documents? And that is where Vector Store comes in. Vector Store are specialized databases designed to store embeddings and perform fast similarity search, which is the core of retrieval augmented generation. Whether you're building a chatbot, a document assistant, or a full scale enterprise knowledge system, Vector Store identifies how quickly you can search, how accurately you can retrieve, and how scalable your system becomes. In LangChain, we have multiple vector store options, but two of the most commonly used are Chroma, a lightweight, local, fast, perfect for prototyping, and FAISS, Facebook's highly optimized similarity search engine for large scale applications. In this video, we'll explore both. We'll take the embeddings we generated earlier, store them in a vector store, and then gradually run semantic search to retrieve relevant content, just like a real RAG pipeline does at scale. So let's dive in. Now that we understand what vector stores are and why they are essential for scalable semantic search, let's look at a practical option that fits perfectly into most LangChain workflows. The first vector store we are going to work with is Chroma. Chroma is built to make working with embeddings incredibly straightforward. It allows us to take our text chunks, convert them into vectors using an embedding model, and store them in a way that supports fast similarity search, all without worrying about heavy infrastructure or complex configuration. This makes Chroma an excellent choice when you are prototyping RAG systems, building local AI assistants, experimenting with document retrieval, or even running small to medium scale production workloads. You can think of it as a plug and play vector store that lets you focus on logic rather than setup. Another important aspect of Chroma is how naturally it fits into the LangChain ecosystem. Once your data is inside Chroma, you can immediately use it with retrievers, chains, and agents. Querying it feels no different than asking questions over your documents, except now the retrieval is driven by semantic meaning rather than exact matches. In this section, we'll take a small collection of text, generate embeddings using a Hugging Face model, store those embeddings inside Chroma, and then run a similarity search to see how the most relevant pieces of information are retrieved. This will give you a very clear mental model of how vector store works in practice and how Chroma acts as the storage and retrieval engine behind a real RAG pipeline. Alright, let's move into the code and see Chroma in action. So for the sake of this implementation, I'm going to install a library here called ChromaDB and then LangChain Chroma. So I've added it in requirements.txt. You can install it, install these two from requirements, or install it separately in your virtual environment too. So let me activate my virtual environment first and then start coding on this. Sorry. Wait. Okay, so my virtual environment is activated. Let me go to the code, and at first from LangChain underscore Chroma, I'm going to import Chroma. Then from LangChain Hugging Face, I am going to import Hugging Face embeddings, and from .env, I'm going to import load.env. So first of all, load the credential here, as I'm going to use my Hugging Face embedding model. So I have created an API key from Hugging Face Hub to use the Hugging Face embedding model here. So you need to paste in that particular API key first into your environment file, and then do the code here. So load.env loads that particular Hugging Face API key into my code here. So I'm going to provide a few text here. So my text is going to be a collection of sentences. So let's say the first text is large language models are trained on massive data sets. The second is large language models, or let's call it LLMs, are particularly trained using transformers. The third sentence is Chroma is a lightweight vector store used in LangChain. And the fourth sentence that I'll have is embeddings convert text into numerical representation. Okay, so these are going to be my 4 sentences here that I'm going to convert into embeddings, and then I will store it into my vector store. So for the embedding model, I'm going to define my Hugging Face embeddings class, and then use this sentence transformer all mini LM LXV2 model from Hugging Face embeddings. Now, once we have this embedding, we're going to create our vector store. So vector store is going to come from Chroma dot from underscore texts. In the text part, I'm going to pass my text variable, all from here, text. Now in the embedding part, I'm going to pass my embedding model that I have here. And then in collection underscore name, since this is going to be saved in our disk, so I'll name it LangChain underscore Chroma underscore demo. Okay, so now this will convert all of this text into embeddings and then store it inside this particular location here as a vector store. Now what I'm going to do is I'm going to pass in my query. So let me ask, tell me more about LLMs. Now what this is going to do is, if I use my vector store similarity search with my query and then ask for maybe our top 2 result, what this is going to do is it is going to convert this query into embeddings as well, and then run a similarity search on each of these embeddings stored in the vector store, and then it will give me the 2 most matched content or answers from the vector store here. So I can just print out the results and then see what happens. So let me run this. So Python, this is 9 vector stores 1 chromadb.py. So now that we see in the result, we have 2 different result here. Basically we have asked for top 2 results here. So in the first case, it's called large language models are particularly trained using transformers, and in the second case, it has large language models are trained on massive data sets. So basically it understands that LLMs refer to large language models from this above context here. So this is how we use Chroma in case of our vector database. So far, we've seen how Chroma helps us store embeddings and perform semantic search in a very simple and developer friendly way. It's lightweight, easy to set up,
and perfect when you're experimenting, prototyping, or working with smaller to medium sized datasets. But as your RAG application grows, a new question starts to appear. What happens when you're no longer dealing with hundreds of or thousands of embeddings, but we're dealing with millions? And that is where FAISS comes into the picture. FAISS, which stands for Facebook AI Similarity Search, is built with one primary goal in mind: fast and scalable similarity search in high dimensional vector spaces. Unlike Chroma, which focuses on ease of use and persistence, FAISS is all about performance and efficiency. Think of it this way: with Chroma, you're working with a vector database that manages storage, collections, and metadata for you. It feels very close to working with a traditional database, just adapted for the vectors. FAISS, on the other hand, behaves more like a high performance search engine for vectors. It doesn't try to be a full database. Instead, it specializes in how quickly and accurately it can find the nearest vectors, even when the dataset becomes extremely large. Another key difference is how they are typically used. Chroma is often used as a persistent vector store, meaning your embeddings can live on disk, reload easily, and integrate smoothly into end-to-end RAG pipelines. FAISS is commonly used when you need very fast similarity search. You're dealing with large-scale embedding datasets, and you want fine-grained control over indexing strategies and performance trade-offs. In real-world RAG systems, FAISS often powers the retrieval layer when scale becomes critical, especially in research or enterprise-level applications. So conceptually, both Chroma and FAISS solve the same problem: storing and searching embeddings, but they do it with different priorities. Chroma prioritizes simplicity, persistence, and developer experience, while FAISS prioritizes speed, scalability, and efficient nearest neighbor search. So in the next part, we'll take this idea and actually implement FAISS in LangChain. So you can see how embeddings move from text into vectors and finally into a high performance retrieval system that sits at the heart of modern RAG architectures.
So for the implementation of FAISS Vector Store, again, I'm going to install this library called FAISS CPU. Again, I pasted it in requirements.py, so you can do it from here. And then I will go to my FAISSVS.py, and then I'm going to start importing now. So from LangChain Hugging Face, I'm going to use the same model as I did earlier. Import Hugging Face embeddings. Then from LangChain underscore community dot vector stores, I'm going to import FAISS. Then from .env, I'm going to import load.env, load the credential first, and then I am going to define some text here. So this will be related to cricket. Let me just paste this so that it will not take any unnecessary time in our video. Let me close this now. Let me also do a word wrap so that you understand what kind of data we have. So this is all about cricket. And then I have 1, 2, 3, 4, 5 text sentences, which is about cricket here. So now I'm going to define my embedding model. Again, I'm going to use the same model, the sentence transformers, all LM, all mini LM, LXV2. Now, while creating vector store, I'm going to do a vector store equals to FAISS dot from texts. And then in the same pattern, I'm going to provide in the text. This is going to be my cricket underscore text. It will come from here. And then along with this, I'm going to pass in my embedding function. So embedding equals to embeddings that I've created here. So once this is created and our embeddings are saved in our vector store, I'll pass in a query, and the query will be maybe who is known as, or who is the god of cricket. Okay, so this is my question. Then what I'm going to do is I'm going to run a similarity search on the vector store. So results equals to vector store dot similarity search. I'll pass in my query, and then maybe I'll only try to retrieve the top one result here, because there can only be one god of cricket. And then in our second text, his name is Sachin Tendulkar here. So it should extract me the exact same sentence from the vector store using the similarity approach. So now if I print my results, and let me rerun this again. So now 2.vs.py. So as you can see, my answer is retrieved, and then the exact sentence that I'm looking for is extracted using the similarity search. So we can even do this for documents. If we have documents, we simply need to do FAISS from documents and then pass in our document here, and the embedding function will be the same. So this is how we can implement FAISS in our in terms of our vector store here.
And that concludes our deep dive into FAISS and how it allows us to store embeddings and perform semantic searches efficiently. We've seen how splitting knowledge into chunks and storing them as vectors makes it easy to retrieve meaningful information even for large datasets.
So far in this series, we've learned how to load data, split it, convert it into embeddings, and store it efficiently inside vector databases. But there's still one missing piece in this entire RAG pipeline. We have questions, or we have knowledge stored somewhere, but how does an AI model know what to fetch when a user asks a question? This is where intelligent retrieval comes into play. In a real world system, you don't want to dump your entire database into the prompt. This would be slow, expensive, and completely impractical. Instead, you need a smart mechanism that can scan through massive amounts of stored information and pull out only the most relevant pieces based on user's intent. Sometimes that information can come from an external knowledge source that updates constantly. Other times, it may live inside your own vector database. And in many scenarios, it's not just about finding the closest match. It's about avoiding repetitive or overly similar results and ensuring diversity in what gets retrieved. In this video, we'll explore how LangChain enables this intelligent selection process. You'll see how context is dynamically fetched, how relevance is measured, and how retrieval quality directly impacts the final answer generated by the LLM. This is the layer that truly transforms embeddings into and vector stores into usable knowledge systems. And once you understand this, building powerful RAG applications become much more intuitive. So let's dive in. But before we jump into different retrieval strategies and their implementations, it is important to understand what actually happens under the hood when a retriever is used. At a lower level, retrieval is all about comparison. When a user asks a question, the query is first converted into same numerical representation, that is an embedding, that we used when storing our documents. Now, we're no longer dealing with raw text, but with points in a high-dimensional vector space. Once the query becomes a vector, the system compares it against all the stored vectors using similarity measures like distance or cosine similarity. The goal is simple. Find the pieces of information that are closest in meaning, not just in wording. But retrieval isn't only about similarity scores. There are additional choices happening behind the scenes. How many results should be fetched? Should the system prioritize the closest match only or balance relevance with variety? Or should result come from a local knowledge base or from a constantly updating external source? This retrieval layer acts as a filter between your stored knowledge and the language model. It decides what the model gets to see and what's get ignored. And because LLMs are highly sensitive to the quality of context they receive, even small improvements at this stage can dramatically improve final answers. Now that we understand how retrievers operate at a foundational level, we can move on to exploring different retrieval approaches and see how LangChain makes each of them easy to implement in practice. We will start with a retrieval scenario where the knowledge doesn't live inside our own documents or vector databases. In many real-world applications, the information we need is public, factual, and constantly evolving. Think of topics like science, technology, history, or general definitions. In such cases, maintaining and updating your own knowledge base doesn't always make sense. Instead, the retriever directly connects to a trusted external knowledge source and pulls relevant information on demand. Conceptually, this works very differently from vector-based retrieval. There are no pre-computed embeddings stored in advance. Instead, when a query comes in, the system searches across a massive, structured repository of human knowledge and retrieves the most relevant articles or sections related to that query. This approach is especially useful when you need an up-to-date or general knowledge, when you don't want the overhead of managing your own dataset, and when the questions are more exploratory or informational in nature. Each retrieved result is returned as a document object, just like documents from files or websites. This consistency is important because it means the retrieved content can be seamlessly passed into chains, prompts, or even combined with other reviewers later on. In the code that follows, you'll see how a simple query can dynamically pull multiple relevant knowledge chunks from a large public source and make them immediately usable inside a LangChain pipeline. This gives your AI system access to a living knowledge base without you having to store or maintain it yourself. So the implementation that we're going to do is the Wikipedia retriever. For the sake of this implementation, I don't need any additional libraries. So I can directly go to my code and then start typing. So from LangChain underscore community dot retrievers, I can import Wikipedia retriever. Now, if I need to define the object for this, I'm going to do retriever equal to Wikipedia retriever. Maybe I'll select the top key results as 2, and then the language I'm going to select is English. So now I just need to pass in my query. Let's call it artificial intelligence. And then basically I can simply invoke my retriever here. So retriever dot invoke query. Now, if you need to see how many documents have been extracted, you can do println docs, and to enumerate across each document, I can do for idoc in enumerate docs. Let me print the page content here or the result content here without the metadata part. So content slash n comma doc dot page underscore content. So this is all I need to do. Let me run my code. So Python 10 retrievers, one Wikipedia retriever.py, and running this. Okay, so I seem to have one more library installed here. So in requirements.txt, you can type in Wikipedia, Wikipedia. So save this. I'm just going to install this from requirements. So pip install -r requirements.txt. So this will be installed inside my virtual environment. And once this is done, I can rerun my code and then check the result here. So we will allow some time for this to be complete, and then we'll continue running our code. Okay, so now this is up installed. Let me clear my terminal and then run my code again, which is Wikipedia retrievers.py. So the first thing that I should see is the number of documents that have been extracted. Simply because I've extracted the top 2 results, it should come as 2. And then I've only selected English language articles from Wikipedia, so it should provide me similar articles from Wikipedia. So let me go to the very top, and then I can see that I have 2 different documents extracted, and the content of first document starts from here, and then we move on to where do we go up to? Terminology, characteristics, intelligent state. We should have 2 different documents here. Let me insert a blank line so that it becomes easier for us to differentiate where these 2 documents are. Okay, so clear the terminal again, and then run the same code. Okay, so the first content seems to be starting from here, and then it goes up to this point. I think we have some padding in terms of the content extraction, and then the second article is extracted from here, and then it goes up to the end of this particular part here. So the retriever, I think, is doing some form of padding to manage the sequence length that the model follows here. So this is how we can use Wikipedia retrievers in LangChain. Now we'll shift from external knowledge sources to a much more common and powerful scenario, retrieving information from your own data. In the example that we'll do, the knowledge doesn't come from the web or public encyclopedia. Instead, it comes from a small, controlled set of documents that represent information you care about. Think of this as your private knowledge base, which can be product documentation, internal notes, or domain-specific content. Before retrieval can happen, this information is first converted into a format that machines can understand semantically. Each piece of text is transformed into a vector representation, capturing its meaning rather than just keywords. These vectors are then stored in a vector database that are built for fast similarity search. Once the data is stored, we introduce a key idea here, turning a vector store into a retriever. So a retriever here acts as a smart interface on top of the vector database. Instead of manually performing similarity searches every time, we ask a retriever a question in plain language. Behind the scenes, it converts the query into a vector, compares it with stored vectors, and returns the most relevant pieces of information. The parameter that controls how many results come back is important. Too few and you might miss useful context, and too many and you might risk overwhelming the model. The retriever helps strike that balance. What's powerful here is that the retrieved results are returned as documents, the same format used throughout LangChain. That means they can be directly plugged into prompts, chains, or full RAG pipelines without any extra transformation. At the end, you'll also be able to see a similarity score being returned. This will give you an insight into how confident the system is about a retrieved result, which is especially useful when debugging or fine-tuning retrieval quality. So this pattern, where we store embeddings and wrap them with a retriever and query them dynamically, forms the backbone of most production-grade RAG systems. So let's go for the implementation and see that in practice now. This implementation, we don't need any additional libraries, but this is kind of what we've already done in our previous video. We've imported our Chroma, we've imported Hugging Face. The main difference here is instead of text like we did in our earlier videos, we are working with our documents, and our content is stored inside our document, and then we have a list of documents in this particular documents variable here. The embedding model is the same, and then creating a vector store from these embedding models, and then these documents is also kind of the stuff that we've already done in our previous video. Now what we're going to do is we're going to create our retriever. So for the retriever, we're going to do vector store dot as underscore retriever. So for this, I'm going to pass in the search keyword arguments, and then here I'm going to pass in k equals to 2, and then I'll define my query. So query can be what is Chroma used for. Now, unlike any other LangChain components, we can invoke this particular retriever here. So I'm going to do results equals to retriever dot invoke, and then pass in my query. Now I can simply print my results here. So now let me run my code. I'm already in my terminal. So if I run this particular vector store retriever.py, then I should see the top two results from these above documents, and then the result should be based on the match between the query and the document present above here. Okay, so let's see the document ID. We have so many more documents here. Almost everything is provided as our answer here. So Chroma is a vector database optimized for LLM based search. We only asked for 2, but it kind of provided us with 4. I think sorry, I did some wrong with the spelling here. So we'll only fetch the top one result in this particular case. Let me clear this up and then run this again. So I should only get one result here. So basically it will be for this particular query, what is Chroma used for, and then my possible answer should be Chroma is a vector database optimized for LLM based search. So let's see if we get that answer or not. So we indeed get that answer here. Chroma is a vector database optimized for LLM based search. Since we only asked for one result, we only got one result here. So this is how we can use our vector store as a retriever in LangChain. Now we'll talk about a retrieval strategy designed specifically to solve one of the most common problems in semantic search, which is redundancy. When we rely on similarity scores, the retriever often returns documents that are very close to each other in meaning. While this may sound ideal, it can actually hurt performance because the language model ends up seeing the same idea repeated multiple times, just phrased slightly differently. This is where maximal marginal relevance or MMR comes into play. MMR works by optimizing two things at the same time. First, how relevant a document is to the user's query, and second, how different that document is from the ones already selected. So instead of selecting all results purely based on similarity of the query, MMR selects the first most relevant document, then carefully chooses the next one by penalizing candidates that are too similar to what's already been picked. In simple terms, MMR asks, is this document useful for answering the question, or does it add something new? And this makes MMR especially powerful in scenarios where documents overlap in meaning, the knowledge base contains paraphrased or repeated content, and you want broader coverage instead of a narrow repetition. The balance between relevance and diversity is adjustable. One parameter controls how importance is given to matching the query, while the other encourages diversity among the results. Tuning this balance helps you shape the quality of retrieved context depending on your use case. The result is a retrieval set that is not only relevant but also informative, complementary, and diverse, which significantly improves how well an LLM can reason over the provided context. And this is why MMR is often preferred in production grade RAG systems where quality or context quality matters as much as context relevance. Now, let's see the implementation. So for this implementation too, we've jumped over some steps here. We are using our FAISS vector store, using our Hugging Face embeddings and then documents. So I have these contents in the form of document and then a single list holding all of these documents inside this. So I also have a Hugging Face embedding model for embedding here. And then what I've done is I've created a vector store from using the face library and then from documents, passing in the document and then the embedding function. What I need to do here is build a retriever here. So for that, what I'm going to do is I'm going to call a retriever object. So create a retriever object and then call vector store dot as underscore retriever. And inside this, I'm going to do search type equals to MMR, which means maximal marginal relevance. And then in terms of search keyword arguments, I'm going to do maybe I will fetch the top 3 result, or I want to fetch the top 3 result. And then inside this, I'm going to pass in lambda underscore mult and then a certain value inside this. So the value inside this particular parameter here goes from 0.0 to 1.0. the meaning of the value or the meaning of the term lambda mult equals to 0.0 means full diversity. It actually ignores relevance completely, which and it is also rarely useful. And the value 1.0 means full relevance. It means it ignores diversity and then it is equivalent to standard similarity search here. So the value in between the balance or the values in between balances the two. The higher the value, the more the retriever prioritizes relevance over diversity, and lower the value, the more it prioritizes diversity among selected results. So for this particular value 0.25 here, it means 25% emphasis on the relevance and 75% emphasis on the diversity. So this encourages the query or the retriever to return results that are still relevant to the query but are more valid and less repetitive. Now I have invoked this retriever using this invoke function and then pass in the query here, and then I can simply print out the result. So now let me run this code and then run this file here 3.mmr.py. It might take some time, but we'll wait for it and then see the result. Okay, so the query was uh, what is LangChain? So what it has done is it has provided this particular answer as my first or prioritized result. But even though the word LangChain is particularly provided in this particular query too, to maintain the variability, it has not returned me this particular uh, document in terms of its response. Instead, it has gone to embedding and then after that it has gone to MMR. So this kind of shows the diversity in our result. If we had simply used a similarity search, it would have probably returned these two results with priority because basically the query as well as the document contains this keyword LangChain here. So this is what maximal marginal relevance do. It introduces diversity in terms of the retrieval process. And that wraps our deep dive into retrievers and the critical role they play in connecting your stored knowledge with LLMs. We explored how information can be fetched from both external and internal sources, how vector-based retrieval works, and how advanced strategies like maximal marginal relevance help us get results that are both relevant and diverse. These components form the backbone of any robust RAG system. And now that we've covered document loading, embedding, vector store, and retriever, we have all the pieces we need. All the pieces to build a complete retrieval augmented generation system. So in the next video, we'll bring everything together and build a RAG system, demonstrating how these components interact to answer real user queries intelligently. We started by understanding how language models work, how to design prompts, how to structure their outputs. Then we learned how to load real-world data, split it into meaningful chunks, convert it into embeddings, and store those embeddings efficiently in vector databases. Finally, we explored retrievers, the intelligence layer that decides what information the models should actually see. Individually, each of these concepts is useful, but together they form something much more powerful. This is where Retrieval Augmented Generation or RAG comes to life. RAG solves one of the biggest limitations of language model. They don't inherently know your data. By combining retrieval with generation, we allow the model to ground its answers in real, up-to-date, and domain-specific knowledge, whether that data comes from documents, websites, or internal databases. In this video, we're not introducing any new theory. Instead, we're going to connect all the dots. You'll see how document loaders, text splitters, embeddings, vector stores, and retrievers work together in a single pipeline. Step by step, we'll build a complete RAG system that takes a user question, retrieves the most relevant context, and generates accurate, grounded responses. If you've been following this series so far, this is where everything finally clicks. So let's build a real RAG application. Okay, so in this video, we're going to implement our RAG system now. So we'll start with import. So from .env, import load.env, and then I'm going to load the credential. Well, my credential contains the API key for grok model as well as the Hugging Face embedding model. So now, first of all, the first task that we're going to do is we'll load a PDF document. So to do that, I'm going to import LangChain underscore community dot document loaders import by PDF loader. And I have a PDF here for this audit report. I'm going to load the same document and then build a rack system around it. So what I'm going to do is I'm going to create a loader object using PyPDF loader class, and then my document name is audit report.pdf. So let me use this loader and then call a load function. Once this PDF document is loaded, what we're going to do is we're going to split the document into chunks. So for task number 2, we're going to split documents into chunks. And to do that, we're going to use from LangChain underscore text splitters import recursive character text splitter. Now I'm going to define this text splitter object and then call this recursive character text splitter class, and then I'm going to define a chunk size. Let's keep the chunk size to about 500, and then a chunk overlap to about 100. Then after this, I'm going to create docs using this splitter object, and then I'm going to split documents inside this. Yes, so this is documents. Yes, okay, documents. Now that this is done too, what we're going to do is in step 3, now we're going to call our embedding model. So create embeddings. Now to create embeddings, we're going to use from LangChain underscore Hugging Face import Hugging Face embeddings, and then my embedding model will be the same that I've been using in my previous video. So embeddings equals to Hugging Face embeddings, and then my model name is sentence transformers all mini LM L6 V2. Now after this, I'm going to store these embeddings in a vector database. So store embeddings in vector database, and for that we're going to use Chroma for now. So in Chroma, what I'm going to do is I'm first going to import Chroma here. So from LangChain underscore Chroma import Chroma, and then I'm going to create a vector store here. So vector store equals to Chroma dot from underscore documents. Now I'll provide my documents here. This will be the docs object that I've created using this splitter object here, and after this I'm going to call the embedding. My embedding will be the embedding model that I've defined here, and then finally a collection name. So the collection name will be RAG collection. Okay, we have done up to the vector store part. Once we have stored our embeddings in our vector store, we are going to define a retriever object. So defining a retriever. So this will be retriever equals to vector store dot as underscore retriever. Here I'm going to do search type equals to MMR. MMR basically means maximal marginal relevance. So MMR basically means maximal marginal relevance. Here we've already talked about it in the previous video. If you haven't seen that video, you can go and check it out to know more about this MMR parameter here. So in search queries, I'm going to maybe generate the top two results only, and then for lambda mult mult, I'm going to pass in 0.5 here. So in order to understand this too, please go to our previous video in this LangChain series. You can easily and clearly understand what this term MMR and then the lambda mult term means here. Okay, once this is done, now in step 6, I'm going to initialize my LLM here. So for the LLM, I'm going to use LangChain Grok, and then from here I'm going to import chat Grok. Now define my model. I'm going to define LLM chat Grok. The model name that I'll place here is llama model, llama 3.3 with 70 billion parameter. Okay, so this is going to be my model for this particular project here. Then what I'm going to do is in step 7, I'm going to create my prompt template. So create prompt template, and to do that I'm going to import LangChain core.prompts import prompt template. We can also use chat prompt template here. If you don't know the variation between the prompt template and the chat prompt template, you need to visit our previous video on prompts and then basically understand it from there. So prompt template, let me define a template here. So the template is provide a string. So the template is like this: you are an AI assistant, use the following context to answer the question. If answer the question if the context or answer is not present, sorry, so if the answer is not present in the context, say you don't know, and then I'm going to pass in the context here. So my context will come from context variable, and then my question will come from the question variable again. And then the model basically needs to provide me an answer. What I'm going to do here is I'm going to do input underscore variables. Then I'll pass in the two variables. First is the context and then second is the question. Okay. So now we are going to build or indicate an output parser here. So let me write output parser definition. And then in this case, we're going to use a simple output parser or str output parsers. So from LangChain core dot output parsers, we need to import str output parser. So we're also going to create an object for this str output parser. This is done too. Now finally, in step 9, we are going to build a chain. So build a RAG chain. So for this RAG chain, what I'm going to do is I'm going to first define a function format underscore docs, then pass in my docs here, and basically I'm going to join my document into a single string here. So dot join doc dot page underscore content for doc in docs. Okay, so this is my function. Now I'll define my RAG chain here. So my RAG chain will indicate that at first I'll pass in my context. So my context will come from a retriever, and then if we have multiple, since we have called for results, it should also be joined into a single string. So I'm going to call the format docs function here. Then I need to pass in the question, and then the question will be just a single query. So as it is here, so yeah, lambda x colon x, just a simple query as it is. Question mbda lambda. Yeah, so now after this I'm going to pass it to my prompt, and after this I'm going to pass it to LLM, and then finally I'm going to pass it to a parser object. So this is my entire RAG chain here. And now what we need to do is, now we need to interact with the bots. So maybe ask a question to the system. So query, I'll ask what is this document mainly about, and then I'll log the response in the response variable. And to invoke this question, I'm going to call on RAGChain dot invoke, and then I'll pass in the query here. So once the query is passed, where does the query go to? So the query basically goes to the question part here, and then from this particular question, retriever is called. So the top two results are called. They are joined into a single string using format docs, and then they are passed to the prompt here. So basically, we now have question as well as context, and then from a prompt, or like after the prompt is prepared, we'll pass it to the LLM chat grok model, and then finally pass it to the parser. Now what I can do is I can simply print my answer here. So print response. It should be in a string because we have used a str output parser at the end. So now let me activate my virtual environment since my code is ready to be run. So scripts and then activate. So my virtual environment is activated. Now let me run the code. So 11.rag and then 1.basic-rag.py. It might take some time because it is a huge document. Everything needs to be converted into embeddings. It needs to be stored in our vector database, and then we're basically asking a question to our system based on the document that we've uploaded, or based on the document that we provided. So we seem to have our answer here. So the answer says that this document appears to be an audit report. Obviously it is an audit report here. And then what else? Mainly about the examination of internal controls, accounting records and financial statement, and the findings and observation resulting from that examination. Okay, what else? Let me ask one more question here. What is this? These are 70. So let me change my question here. For 2006 2007, INCAP increased the number of donors from 12 to 18. Okay, so how many donors were included by, okay, what is it? It's INCAP. Yeah, INCAP for 2006 2007, or will do 2006 7 year. So yeah, let me run this code again. It should find me the answer from this particular document, and then basically give me that the donors, maybe it will provide me that the donors are 18, or maybe it will say that INCAP increased the number of donors from 12 to 18 or something like that. Well, we'll find it out. Okay, so in the answer, the model actually got confused, but it did not hallucinate and then provide any random answer. Instead, it said it didn't know. The provided context does not mention the number of donors included by INCAP for 2006 or 7. It only mentions that SICA accounted for 70% of all voluntary contributions in the biennium and recommends that INCAP. Okay, so we'll ask something else. If there is a table here, we can ask it from the table. We'll ask the in-caps total income in 2004-2005. So what is in-caps total income in 2004, sorry, 2004 2005? We will not say is, we'll say was. Again, run this code. So based on the document here, it basically went from $807,400 in 2004-2005, but we'll find out if the model can actually find that answer or not. The context does not provide the total income of in-cap for 2004-2005, only specific components of income such as miscellaneous or other. Well, it did find out that and quota income 807,400. It did find this particular income from our document, but the model hesitated from hallucinating and then providing any random answer here. Well, we'll ask something else here. So the third question is going to be something like this. Can you find me the, or like we'll ask straightly. So who is the god of machine learning? The model should not hallucinate and then provide me an answer like something I don't know. Okay, so it says I don't know. The provided context does not mention anything about the god of machine learning. So if it can find any kind of answer here, it does try to provide me that answer. But if it doesn't know, the model or the rack system does not hallucinate. It simply says I don't know, just because of the prompt that I provided here. Okay, so this is the end to this basic rack system. Whatever we've done here, we first loaded a PDF document using a PyPDF loader. We've splitted the document into chunks using recursive character text splitter. Each chunk size is 500, and then the chunk overlap is 100. Then we've created embeddings using this Hugging Face embedding model. We've stored these embeddings into a Chroma vector store, and then we've used that same vector store as a retriever here. The source type is maximum marginal relevance. The top two searches are ordered here, and then we have used just ChatGrok model, or inside this we've used this llama model as an LLM. We provided a prompt here, and then a string output parser. In terms of the chain, we have provided the context using this retriever as well as this format docs function, where the contexts are merged into a single string, and then we passed our question here. So at the end, we've invoked this chain and then passed our question to it and then generated the response. And with that, we built our first complete retrieval augmented generation system. But this is not the end, it's just the beginning. What you've seen in this video is the foundation of intelligent systems that can reason over documents, ground their answers in real data, and evolve far beyond simple question answering. From here, we can explore more advanced RAG variations, improve retrieval strategies, and build systems that truly understand context. So in the upcoming videos, we'll take this further by adding contextual conversation, memory, and more intelligent retrieval flows, transforming this basic RAG setup into a system that feels natural, adaptive, and production ready. So if you followed this series up to this point, you now have all the core building blocks. What comes next is about refinement, scale, and intelligence. Imagine you're building a RAG system for a client or for your own knowledge application. In the earlier videos, we created a basic RAG pipeline where you query a PDF, split it into chunks, embed the chunks, store them in a vector store, retrieve the most relevant chunks, and then feed them to a language model to get an answer. It worked well, where you got answers from your documents and the system was fast and functional. But there's a major limitation. When the model gives you an answer, you have no way of knowing which part of your document it actually used. The model could be hallucinating, or it might have picked a chunk you did not intend. This is fine for a quick experiment, but in real-world application, especially when building AI tools for knowledge, work, education, or enterprise, this lack of transparency is a big problem. Users and developers need explainable AI, answers that come with evidence. Ideally, the system should tell you which page in your PDF the information came from, which exact chunk of text was used to answer the question, and even when the multiple sources were used, if the answer is composed from more than one part. This is what we're tackling in today's episode. We're moving from basic RAG to a source-aware RAG, or what you can think of as an explainable RAG. Here, every answer your model generates will be accompanied by the context it actually used, along with metadata like page numbers or chunk references. This not only improves trustworthiness, but also helps developers and users verify, audit, and understand the answers. So in this video, we'll build a pipeline that loads a PDF and splits it into manageable chunks, embeds the chunk and stores them in a query vector, retrieves the most relevant chunks for a query, feed only the retrieved chunk to the LLM, and returns both the answer and the sources used. And by the end of this, you'll have a RAG system that is not only powerful, but also transparent and explainable, taking your knowledge application to a more professional and reliable level. First, we're going to do from .env import load.env. So this will be used to load our credential, as we already know. So in step 1, we're going to load a PDF. So to do that, from LangChain underscore community dot document loaders, I am going to import PyPDF loader, define the loader object, define my file name, then I'm going to do documents equals to loader.load. In number 2, I'm going to split my document into chunks. And to do that, I'm going to use LangChain text splitters, and then inside it, I'm going to import a recursive LangChain underscore text splitters, import a recursive character text splitter. Let me define my splitter function here. So text splitter equals to recursive character text splitter. The chunk size is, okay, let's call it 500, and then the chunk overlap, let's call it 100. Now in step 3, I'm going to create embeddings. So I'm going to import Hugging Face embeddings from LangChain underscore Hugging Face. And then I'm going to define an embedding model. The model name is going to be sentence transformers all mini LM L6 V2. In step number 4, I'm going to store embeddings in Chroma. And in vector store object, I'm going to define Chroma dot from underscore documents. I'm going to pass in my documents from chunks. Documents are chunks. So what have I defined it here? Okay, so I might have missed this. So after my splitter, I need to split my text into chunks here. So this is going to be text splitter dot split documents, and then I'm going to do documents here. Now here I'm going to pass in chunks as documents. As my embedding, I'm going to pass embeddings, and in place of collection name, I'm going to pass source aware rag. I'm going to run a similarity search. So here I'm going to pass in my query. We'll ask what is the report about. In place of retrieved docs, I'm going to do vector store dot similarity search, pass in my query, and then I'm going to extract top 3 results here. In the next part, I'm going to build context plus source. So in terms of my result, let me put down context text as a variable and then source as a list here. So for I doc in enumerate, I've extracted top 3 results, right? So I'll run a loop on it. Retrieve docs. What I can do is page equals to doc dot metadata dot get, and then I can extract page here. If I don't find any page, let me give NA. And similarly, in terms of source, I can do doc dot metadata dot get, and in place of source, I can provide source. If nothing is present, then a default value can be PDF. Now, now for context text, I'm going to just add whatever thing I have in this page content here. So content plus equals to F. So chunk I plus 1 plus n doc dot page underscore content. And for source, I can do source dot append. So this can be sources. Here I'll put sources. So in the append function, what I can append is I can append the chunk number. So the chunk can be I plus 1, and then for page, it can be the page that I've extracted above here. Then for source, I can do source just from this variable here, and then for content, I can do doc dot page underscore content. Now I can define my prompt. So 7 is going to be prompt lm with context. So for this, I'm going to import from LangChain Grok. I'm going to import chat Grok. from LangChain core dot prompts, I am going to import prompt template, and from LangChain core dot output parsers, I'm going to import str output parser. Let me define my LLM model, which will come from ChatGrok. ChatGrok, and then the model that I'll be using will be Llama 3.3 model. Okay, now after this, what I can do is I can define a prompt using my prompt template. So my prompt will come from template class. Then inside this, I'll first define my template. So answer the question only using the context below. Also provide the actual chunk during a retrieval along with the page number of the document where I can find that chunk. Along with this, what I would like to define is I'd like to define my context. So my context will be context. My question will be question, and then okay, what else? I think that will be sufficient. And then I'm going to define my input variables. So my input variables will be context and then question. Now what I can do is I can define my parser. So my parser is going to come from str output parser, and I'll define my chain. My chain will be prompt LLM, and then parser. And finally, I can invoke. So basically do chain dot invoke, pass in the context text. So the context underscore text will come from context text, and then my question QUESTR, the question will come from the query. So finally, I can print my answer here. So let me just print answer, and then for sources, what I can do is for src in sources. So I can first print out the chunk. So chunk is going to come from src chunk, and then its page number is going to come from src and then page. Then I can also print its content. So this will come from src content, and then let me print a horizontal line here. So now this is all my code. At first, what we've done is we have retrieved our chunk from this vector store using this query here. The top three results, the actual content, the page number, as well as the source are extracted. The page number and source are extracted from the metadata, while the actual chunk is extracted from the page content, and then they appended into this sources list. Then I have my model, and then using my model and then using a prompt template, I'm passing it to an LLM and then a str output parser, and then getting my answer here. So there was a slight mistake in my code here. I had written context underscore test, but it should be context here. So once I run this code, I can see that my question was actually what is the report about. Where is my question? So yeah, it says that the report is about the audit of financial statement of institution of nutrition of Central America and Panama. In cap, it extracts the following chunk for me. So chunk 1 and then chunk 2 and chunk 3. Uh, so whenever I try to print my sources, it not only provides me the actual answer, but the chunk part as well as the page number where this particular chunk is present. So this now becomes much more explainable for this particular answer here in terms of its source, meaning in understanding where the source is actually coming from. So what we built today is a big step forward from our basic RAG system. We didn't just ask the model for answers, we asked it to show its work. By attaching page numbers and the exact document chunks to use to generate each response, we made our RAG pipeline transparent, verifiable, and trustworthy. So this is the foundation of what real-world production-ready RAG systems look like. Systems where users can trace answers back to their original sources instead of blindly trusting a black box. But this is still just one piece of the puzzle. Right now, our interaction is stateless. Every question is treated in isolation, and our interface lives in the terminal. That's fine for learning and experimentation, but not for real users. In the next part of this series, we're going to take this even further. We'll move from the terminal to a Streamlit-based chat interface, build a proper chat window, and introduce conversation memory so the system can understand follow-up questions, context, and intent across multiple turns. And that is where RAG starts to feel like a script and feel less like a script and more like an intelligent assistant. So this isn't the end, it's the beginning of building interactive, explainable, and conversational AI systems. In the last video, we took our RAG system one step further. We didn't just retrieve answers anymore, we made the system explainable. We saw where the answer came from, which page of the PDF it was extracted from, and which exact chunk was used as context. But there was still one big limitation. Every time we asked a question, the system treated it as a brand new request. No memory, no understanding of what we asked before, and no ability to handle follow-up questions like explain that again or what about the next part. And that's a serious problem because real users don't talk to AI in isolated prompts. They talk in conversations. So in this video, we're going to fix that. We're building a conversational RAG system where retrieval still happens from your documents, but now the model also understands the entire conversation history. And the most important part, we're not going to rely on any deprecated chains, hidden abstractions, or black box helpers. Instead, we'll implement everything manually and explicitly. We'll manage chat history using messages. We'll inject conversation history directly into the prompts. And we'll combine that with a retrieval in a clean, future-proof way. And by the end of this video, you'll have a RAG system that can handle follow-up questions naturally, maintain conversational context, and still stay grounded in your documents. So without any delay, let's start building. So at the beginning, we're going to write all of our imports. The first import will be our PyPDF loader. Then we'll import chat group. Then a list. A base message, a human message, and AI message, as well as a system message. Then we'll import chat prompt template and then a messages placeholder. After that, to break our document into chunks, we'll again use a recursive character text splitter. For our vector store, we're going to use Chroma. For embedding, we're going to use Hugging Face embeddings. And to load our credential, we are going to do load.env. Okay, so now, first of all, we'll load our document using the PyPDF loader class. The file name is audit report.pdf. Now we'll do documents equals to loader.load. Let me also define my model. So it is again going to be a llama model. Now I'm going to define my splitter object. Let me define the chunk size as 1000 and then the chunk overlap to be around 100. Then I'm going to break my document into chunks using splitter object here, splitter.split underscore documents, and then I'm going to pass in my documents from up here. Now I'm going to define my embedding model. My embedding model will come from Hugging Face embeddings, and then the model that I'm going to use is sentence transformers all mini LM L6 V2. This is the same model that we have been using in our previous videos too. Now I'm going to create a vector store. Using Chroma, where I will pass my documents as chunks and then my embedding as embedding model that I've just defined above. Then I'll now define a retriever object. So I'll use the vector store as a retriever, and here the search quirks is going to be let me fetch like top four result from the vector store. Now move to defining the prompt using chat prompt template, and chat prompt template I'm going to do from messages here, and inside this I'm first going to type a system message. So the system message is going to be with a content the content is going to be something like this: you are a helpful AI assistant, answer strictly from the provided context. If the answer is not present in the context, just say you don't know. After this, I'm going to define a message placeholder. Inside this message placeholder, we define a variable name. The variable name, I'll keep it at chat history. And then inside this, let me define a human context double slash n and then question will be placed as input. So this is going to be my prompt for this video. Now for the conversational RAG part, I'm going to define it into a function. So conversational RAG, the parameters here will be user input, which will be in the form of string, and then a chat history. This will be in the form of list and then a base message. Now inside this function, first of all, we'll retrieve documents using our retriever. So retriever dot invoke user input. Then in the context, I'm going to join my context. Basically, what can I do here? So let me do something like this. I'll define a page. Then page will come from d.metadata.get page, or by default it will provide an A if not found. And inside this, I'll again do a line break and then do d.page underscore content for d in docs. After this, inside this function, I'm going to build a prompt. So I'm going to do that using prompt.invoke. And inside this, let me keep a curly bracket. Input will come from user underscore input. What else? This, yeah, user underscore input. The context, I think it's not input. Okay, so the context is going to be from context that I've just prepared earlier. And after this, the chat history is going to come from chat history variable. Then I'm going to invoke the LLM with these messages that I've just prepared, or with the prompt that I've just prepared, and then I'm going to return response, docs. So here, before calling this function, I'm going to build a list of base messages called chat history here, base message, and then this is going to be an empty list for now. So let's say conversational RAG. I'll keep this inside a loop for continued conversation, and then ask for the user input. So for the user input, I'll just say you, and then to break out from the loop, I'll keep one condition. So if user input dot lower equals to exit, I'll just do break, or else what we can do is we can append our user input inside the chat history. So chat history dot append, I'm going to keep it as a human message, and the content of the human message is going to be the user input. Now after this, I'm going to call the conversational RAG function. I'm going to pass in the user input as well as the chat history from there. So chat history, and since it returns two different stuffs, responses and docs, I'm going to do responses. I actually don't need the docs if I don't want to show the sources, but anyway, I'll keep it keep it for now. So responses comma sources equals to conversational RAG function called. Now whatever response we get from the model, I'm going to add it or append it inside my chat history again. Dot append. So this will be appended as an AI message, and then its content is going to be the response dot content part, and then I'm going to print whatever the AI prints or AI provides, which is comma response dot content responses dot content, and then responses dot content. Okay, so if you also want to see the source, you can just print out the source here. Basically the source will also be a list, so be careful. You might need to loop over the sources if you want to print out, but I'm not doing that right now. Now I can simply run my code. So Python 11 rag 3 memory rag.py. It seems that I made a mistake here, so let me go to the model definition part or the LLM definition part. So inside this, I should have placed it inside the model parameter. Let me clear the log and then run it again. So the system is running. It has printed me this particular part, conversational RAG here, and then I'm inside this loop here. So if I just hit break, sorry, if I just hit exit, then it will exit from the system. Let me run this again and then start and interacting with that particular system, and then check if the memory we have implemented in this does hold up in the conversation 2 or not. Okay, so now that the system is running again, what I can do is I can say, hi, my name is John, and I would like to ask you what this document is about. So the AI says that the document appears to be an audit report of the institution or Institute of Nutrition of Central America and Panama, INCAP. Okay, that is all. It discusses audit findings, internal controls, and governance arrangement, as well as a recommendation for improvement. Okay, tell me about that last part, recommendations one. So the last part you mentioned is follow up to 2004-5 recommendation, which is paragraph 56-62. However, the text for those paragraphs is not provided in the context of file. Okay, so we'll discuss or we'll ask what else. Tell me about the audit findings. So yeah, the audit findings are quite long, but what I want to check here is, does it have a form of memory or not? Because in the initial query, I had passed my name here too. So here what I can ask is, from our conversation, can you remember my name and tell me what my first question was about. So it does tell me my name. It does know my name because it says your name is John and your first question was about what the document is about. Okay, and after that What did I ask you? After the first question about the document, you asked me to tell you about the recommendation one part, but then you asked me to tell you about the uh, audit findings, and then you asked me to remember your name and tell you what the question was about. And after that, you asked me, after that, what did I ask you? So it does have its memory preserved, but where is that memory preserved here? That particular memory is preserved here in the chat history. So until and unless this particular chat history variable is alive and then is being processed inside this particular loop, the system does have its memory. But again, this particular memory is only confined within one particular session. If I hit exit, so if I hit exit and then the system breaks up, and then if I run this, if I run the code again and then I ask my name, since now the chat history is empty, whenever this particular code is run again, now it does not remember my name at all. But there are workaround to save those conversations in the databases too. So we'll do that in the upcoming videos. But for now, we'll verify uh, whether it remembers my name between sessions here. So do you remember my name? So it says I don't know. So basically, what we did here was implement a form of memory uh, for a continued conversation for the user into the system instead of just one prompt question answers. So with this, we've taken another solid step forward in building truly usable RAG systems. We now have a conversational setup where the model doesn't just answer isolated questions, but understands the flow of the conversation and response in context, while still grounding every answer in retrieved documents. So this is the point where RAG starts to feel practical, not just experimental. But we're still not done here. Right now, our conversation lives only in the memory while the program is running. The moment we restart the app, everything is gone. So in the next video, we're going to fix that. We'll build a ChatGPT style session management where conversations are stored in a database, automatically reloaded when a user comes back, and continued exactly from where they left off. And that's when we move from demos to real production ready AI systems. We are going to build a chat style RAG application where conversations persist across multiple turns, just like in ChatGPT. Each user interaction becomes part of a growing conversation, and that conversation directly influences how the model understands and answers future questions. Even more importantly, we're not just keeping this memory in RAM. We're introducing database-backed session management, which means you can start a brand new chat at any time, or you can switch between older conversations, and your chat history or entire chat history is restored exactly where you left off, just like in ChatGPT or Gemini. To make this practical and usable, we'll wrap everything inside a Streamlit interface, complete with a navigation sidebar for managing multiple chats. And under the hood, we'll combine document retrieval, conversational context, and persistent storage into a clean pipeline. And by the end of this video, you won't just have a RAG model, but you'll have a production style conversational RAG system that looks and behaves like a real world AI applications that we are using daily. So let's start building. The quite can be quite long, so follow along and then pause and repeat it if you have any errors. So we'll start with importing Streamlit. And for that, what I want you to do is go to requirements and then pip install Streamlit inside this, or basically add it in requirements and then install it from there. So I want you to install Streamlit, as it is going to be our front end for our chatbot. So first of all, I'm importing Streamlit as st. Then let me import SQLite 3 for database. I'm going to import uuid. This will be used for something that I'll show you later on. So from typing, let's import a list. This will be for chat history, and from .env let's import load.env. This will be for loading our credential for our chat grok model as well as our embedding model from Hugging Face. Now onto the LangChain components. So from LangChain underscore community dot document loaders, I want to import the PyPDF loader at first. Then from LangChain text splitters, I want to import recursive character text splitter. Similarly, from LangChain community dot vector stores, I want to import Chroma. And from LangChain underscore Hugging Face, I want to import Hugging Face embeddings. And similarly, from LangChain underscore group, I want to import chat grok. Some more imports coming on the way. So from LangChain underscore core dot messages, I am going to make multiple imports here. So let me keep it in this way. So the first will be our base message. The second will be a human message. The third will be our AI message. And then the fourth will be our system message. And along with this, from LangChain underscore core dot prompts, I am going to import chat prompt template and then a messages placeholder. Okay, so almost all the imports are done. First of all, we are going to load our credentials. So for that, I'm going to do load.env. Now we'll work on the database part first. So for the connection, I'm going to do SQLite3.connect connect, then provide our database name. So let me call it chat underscore memory1.db, and I'll do check same thread equals to false. Then once the database is created, I need to create my table. So cursor dot I first need to create a cursor object here. So cursor equals to connection dot cursor function. Now using this cursor object, I can do cursor dot execute, and then I can actually run my query here. Okay, so my query is going to be create table if not exists. I'll provide chat history, or the table name will be chat history. The first component will be session ID. This will be in text. The second component will be role. This will also be a text. And then the third component will be content, and this will also be a text. So this particular query will create my table, and then based on this, I'm going to do connection dot commit. So now my database will also be created, as well as my table will also be created inside this particular database here. Now after this, I'm going to create some helper functions to save our data as well as load our data. So the first function is going to be save message. I'll provide a session ID in the form of string. I'll provide role in the form of string as well as content in the form of string. Then inside this particular function, I'll have cursor dot execute. Basically, I'll write an insertion query. So insert into chat underscore history, and then my values will be question mark, comma, question mark, comma, question mark, and then all of these values will actually come from session ID, role, and then content. Then I will do connection dot commit again. This is for save message. Now I'm going to do the same for load message. So or load chat history. and I'll provide a session ID here in the form of string, and then this is going to return me a list of base message. Inside this, I'm going to again execute a query. So cursor.execute. Let me write my query. So select role, comma content from chat underscore history, where session underscore ID equals to question mark. And this particular session ID is going to come from session ID here. Now, since we are fetching multiple rows here, so I'll write rows equals to cursor dot fetch all. Fetch all is a function. Now I'll create a chat history, a placeholder where I can save my chat history. So list of base message. This is now going to be an empty list for now. So I'm going to iterate it over rows. So for role, comma content in rows, I'll check if role equals to human. If role equals to human, sorry, this should be RLE role. Okay, so if role equals to human, we'll do history dot append, and then I'll provide a human message with the content, as content. Similarly, LF role equals to AI. I'm going to append the same message, history dot append AI message, and this is going to be stored as content equals to content again. And then I'm simply going to return history once all the rows are read. After this, one more function to get all the stored sessions. So the function name is going to be get all sessions. Again, cursor dot execute. So the query is going to be select distinct session underscore ID from chat underscore history, and then I will order by row ID, and then it is going to be in descending order. So I will return row 0 for row in cursor dot fetch all. Okay, so this completes the database helper functions part. Next, we are going to work on the Streamlit configurations part here. Configurations. So first of all, I'm going to do stringlit.setPageConfig, and then inside this, I'm going to do page title. Page title can be a conversational RAG, and then the layout used here will be a white layout. After this, I'm going to provide a title. So st.title is conversational RAG with memory. Now, let me also define the sidebar part here. So for sidebar, I'm going to do st.sidebar.title, and then the sidebar title will be chats. Now, after this, for session management, I'm going to do if session underscore ID is not present in st.session underscore state. I'm going to do st.session state dot session ID equals to string form of uuid dot uuid4. Similarly, st.sessionState.chat_history is going to be an empty list. I'll also have a button that when pressed adds a new chat. So for that, st.sidebar.button. So this will be for new chat. If this is pressed, then again I'm going to do the same thing as above. I'll create a new session ID for this. Session_ID is going to be created again using that UUID class dot UUID4, and after this st.sessionState.chat_history equals to empty list. Now to load all the previous conversations, I'm going to have a markdown here. So st.sidebar.markdown, let's call it previous conversations. And here what I can do is I can call this get all session functions and then basically get a list here in which I can iterate. So for SID in get all sessions, so if st.sidebar.button and then the text of this button, I'm only going to keep this 7 characters from our session ID. Okay, 7 characters from the session ID. What I'm going to do is if this is present, or like if I am reading from each session, then st.sessionState.session_ID equals to SID and st.sessionState.chat_history equals to load chat history, and then I'll provide the session ID here. So if I go to load chat history, then basically based on a certain session ID, I can generate a role and content from here. So everything seems to be done, and then once this is done, I'm going to set session_ID equals to st.sessionState.sessionID. So again, the particular session ID can come from anywhere. It can come from this particular part, it can come from this particular part, or it can come from this particular part here. It can come from any part. We'll go to our LangChain component part. So first I'm going to load an index our PDF here for the RAG model, and for this what I'm going to do is I'm going to cache this particular resource here. So the first resource is the load_vector store. So once the vector store is loaded, it needs to be cached throughout the session here. So I'll call py_pdf loader for this one, and then I'll provide in the PDF file that we have been using, the audit report.pdf. Now I can do document equal to loader.load. So this will only be loaded once whenever we've started our application. So I'm also going to define a splitter. So the splitter will come from recursive character text splitter. I'll provide a chunk_size. The chunk size will be 1000, and then I'll also provide a chunk_overlap, and then this will be around 150. Now I'm going to break my documents into chunks. So I'm going to use the splitter dot split_documents, then provide the document here. Once this is done, define my embedding model. So my embedding model is going to come from Hugging Face embeddings. We will use the same model that we have been using. So model name equals to sentence transformers all LM L6 V2. So this is the model that we have been using from very earlier. Now I'm going to do vector store equals to Chroma dot from_documents. So here my documents is going to be my chunks, and then my embedding Embedding is going to be the embedding object that I've created earlier using Hugging Face embedding. And finally, I'm going to return a vector store. So all of this part will run only once, and then that particular same stuff will be used throughout that particular session in the application here. So now what we're going to do is we're going to define a vector store, and then that can be basically done calling this load vector store function from here. After this, I'm going to call our retriever class or retriever object, and then this will be done using vector store dot as underscore retriever. Vector store dot as retriever, and then from the search parameters, I'm going to provide or I'm going to ask the model to generate the top 4 results here. So k equals to 4. Once this is also done, I can define my LLM model here. So LLM model is going to come from ChatGrok. Again, I'm going to be using the same model, the same llama model that we had been using since quite some time in this tutorial here, 70 million. Now let me define my prompt. So my prompt is going to come from chat prompt template, and then from underscore messages, and inside this I'm going to keep a list, and then inside the list, first of all, I'll have a system message. The system message will basically have the following content. So content equals to let's say you are a helpful AI assistant. Answer strictly from the provided context. If the answer is not present, just say you don't know. Okay, so this will be my first message inside my prompt. Then after the system message, I'll have a message placeholder for my chat history. So here the variable name will be chat underscore history, and then I'll also have a human message inside this. So a round bracket, and then let me provide a role first human, and then basically provide in the context. So the context will come from the context placeholder, and then a question will come from the question placeholder, or we'll call it input here for now. Input. My prompt is also created, or my prompt template is also defined. Now what I'm going to do is I'm going to invoke this conversational RAG function. So def conversational RAG, I'll pass in the user input, which will be in the form of string. Then I'll pass in the chat history, which will be a list, HISTORY. It will be a list, and then list of base message. So base message. Then I'm going to do docs equals to retriever dot invoke, and then user input. What this is going to do is, based on the query that I provide, it is going to retrieve chunks or the top 4 chunks from this particular retriever object that I have here. Now I'm going to join in the context, but I don't think I need to do this. Basically, I have the context here, right? So what I can do directly, or no, I need to join in the context because I need to provide it into the prompt. So Let's do something. So I'll insert two blank lines dot join function, and then inside this join function I'm going to add page. So d dot metadata, I'm going to get the page number from where the context is being extracted. If we have a page, then I'll provide a page. If we don't have a page, then I'll just give a default value here. Then again add a line break and then do d dot page underscore content. Now for my messages part, I'm going to do prompt dot invoke. Then I'll pass in input as user input. I'll pass in the context as context, and then I'll pass in the chat underscore history as chat underscore history. So I seem to have missed something. I need to do for D in docs here. Okay, so this particular part is also complete. Now I need to invoke my model. So for that, I'm going to do response equals to llm dot invoke, and then pass in my messages that I've prepared from my prompt. And then finally, I'm going to return response as well as the docs part. So this is done. Now, whenever we switch session or like we load chat history, we need to define the logic for that too. So for that, what I'm going to do is if not st.session st.session state, if not st.session state dot chat history. So if this is not present, then I'm going to do st.session state dot chat history, chat underscore history equals to load chat history, and then provide a session ID here. Session ID. Now for the chat window part, let me write chat window part. So for the chat window part, I'm going to do for message in st dot session state dot chat history. So if I have multi-turn conversation in my chat history, then I'm going to check what the role is. So if is instance message is a human message, then I can write st dot chat underscore message and then name it user, and then for user I'm going to write a message dot content. So I'll also do elif is instance message dot AI message. If it is an AI message, then st dot chat message, then I'll call it assistant or just call it AI, and then dot write message dot content. Now if a user provides an input, I'm going to log it in user input. So st dot chat underscore input, and then I'll give a placeholder ask or question from a PDF. So if user has provided an input and then submitted the input, so I'll first write the user message in the chat message as a chat message in the user role dot write user underscore input. Then I'm going to save this message in my database. So I will generate a session ID or like whatever session ID I have. In that particular session ID, I'm going to log a human message for this particular user input, or I'm going to save this user input as a human message. Then st dot session state dot chat underscore history, I'm going to append this new message in my chat history. So chat history dot append human message, and then the content is going to be user underscore input. Once this is done, we'll get our response as well as sources. We might not use sources here, but anyway, so we'll call the conversational RAG function and then pass in the user input first, and then our chat history, st.session_state.chat underscore history. Okay, now so we have some response from the model. So first of all, I'm going to save that as an assistant message or AI message. So we'll call it AI dot write, and then I'll write the response dot content part. And after this, I'm going to save the same message in my database. Save message. I'll pass in the session ID. I'll pass in AI, and then basically save the response dot content underscore AI role. Now I'm going to do st dot session underscore state dot chat history dot append, and then I'm going to append an AI message in my chat history whose content is going to be response dot content. Okay, so the code is almost complete. So whatever we've done here, we'll just go through this. First of all, we've used some import, loaded the credential. Then for the database part, we have tried to connect to this particular chat memory 1 DB. If that database is not present, it will be created. And then after that, if the table is not present inside this database, so this particular chat history table will be created. For saving message, I have defined a helper function here to save the session ID, role, and content. To load the chat history, I've again created a helper function which will return me back the chat history that has been saved into the database for a particular session ID. Then I also have another function to get all the sessions, and the database part is almost done up to this point. Then for the Streamlit configuration, I have set page config, and then page title is conversational RAG. I've also placed a title here, and then I have a sidebar with a title chats. Now for an individual session or for a new session, I have created an empty chat history as well as a unique session ID. And I've also tried to load the previous conversations using this get all session functions here. So that is also done. And then the session ID is loaded from the get all sessions function, and then the chat history is loaded using load chat history function by passing the session ID inside it. Yeah. Okay, so this is also done. Now no matter where the session ID comes from, a valid ID is maintained. Now for the LangChain part, I have used this function as a cache resource. Use the loader object with the help of PyPDF loader class, and then basically loaded my document, split it into chunks, and then created a vector store using Chroma, and then these chunks as well as the embedding model, and then basically return the vector store. So a vector store is created, and then the vector store is used as a retriever here. So I have a retriever object too. Then comes my chat grok model, or basically the llama model. I've created a prompt from a chat prompt template. We basically pass in a chat history in the middle, as well as add new context as well as the user input in this particular place. So now for the conversation RAG model, I have retrieved the documents based on the user input from the vector store, and then I have appended them all into one single string. Now my prompt is in the form of this particular form here, including input, context, and chat history. Then I've invoked that particular prompt and then returned the response as well as document. So whenever a chat is loaded, it is loaded using a session ID, and for a particular session chat, I need to show all the conversations. So for that, I have looked around this chat history here, and then basically I have two roles, the user message as well as the AI message, and then showed them accordingly here. We provide this user input as well as the chat history to this conversation RAG function, and it will return me the response and docs, and then I have basically printed the response as an AI message in my chat window as well as saved it in my database too. So this is all for the code. Now I hope I don't have any errors, so let me run this code. So I can do streamlit run and then basically provide the file name. It is inside this folder called rag here, and then the file name is for database memory rag.py. So let's start the project. Okay, the network URL is provided and then the system is running in this particular window. So it will take some time for everything to be set up, and then once it runs, I'll show you what kind of system we've made. Okay, so this particular window is open. We have a sidebar with chats as heading, new chat, and then we also have previous conversations. But since we are doing it for the first time, so we don't have anything. The load vector store function is used as a cache resource. So for the very first run, or like whenever we run for the very first time, that particular function is called. Okay, so we do have some error. So let me check what the error is. So it is in line 160 and then line 47. Line 47. So let me check what happened in line 47. So session ID, okay. Line number, let me pull it a bit down. Line number 47. What did we do wrong here? So select a role as well as content from chat history where session ID equals to something, and then I passed a session ID here. Let me again see the error. So the load underscore chat underscore history, and then it is inside this function. What does it say? Session ID, session ID, session ID, incorrect. Number of bindings applied. Let's see the error here. The error says incorrect number of bindings applied. The current use is 1 and there are 36 applied. Okay, so let's verify this error and then see what we've made wrong here. Two errors here. So the first error that I was doing is I should have inserted a comma inside this load chat history function. So it should be a comma along with the session ID as well as the comma at the end. And somewhere down here, where was that? Let's see. So probably where we have written this particular part. So somewhere down here, instead of writing right, I had written wrote. So make sure it's all right here, okay? And along with this, it's right here. So now we can actually run this code. So Python, I've only I've already tried this. So not Python, it should be Streamlit run 11 rag mem database memory rag.py. So I've already tried this rag like I said, so let me close this and then we'll start from the very beginning. We already have some conversations in the database, and mainly it should load those two sessions that I've stored in the database. So here the load vector store will always run in the beginning as a cache resource. I have two different conversations as a previous conversation. So these two conversation sessions are actually loaded from the database, and then they are loaded from this particular function here, from get all session functions. Where was that? And then I have iterated with that get all session functions here. So yeah, with this particular part, no, not this part, sorry. Where was that? So yeah, it is being displayed from this particular portion here. So now let's go to our previous session conversation. So it does load the conversation that I had, and then I can continue the conversation here. So in the first query, I had provided it my name. So let me just ask what is my name, and then it should tell me that my name is John here. And in the second conversation, where I had said, hello, help me with this PDF, and then it asked me for the issue to address, and then I said, my name is Abhishek, can you tell me what this document is about? It gave me the answer. And then now if I ask what is my name, so for this particular session, my name is Abhishek here, so it does reflect my name. So it does have its own history, a session specific history, as well as these two session conversations are stored in the database. So this is just like using ChatGPT, where we can start a new chat and then start talking to it. So hello, this is a programmer asking you to help me with the code that I am building for a rack system. Basically, it doesn't it does not have any idea about rack system from that particular document, so probably it will say I don't know. So yeah, it says I don't know how to help you with your rack system, as there is no relevant information provided about the code or the system you're building. The context appears to be related to accounting and financial reporting. And then if I ask, does it contain any maybe tutorials on explainable AI? So, the content does not provide any explainable tutorials on AI. And then if I ask what is RAG, it should say I don't know. So it does says I don't know, and then I have created my third session as well. So this is how you build a chat-based system in RAG, but the chat history is saved in the database here, and then you can extract that particular chat history anytime you want and then continue the conversation there. Up until now in this series, we've been building retrieval augmented generation step by step. We started simple, loading a single document, splitting it into chunks, embedding it, storing it in a vector database, and finally querying it using an LLM. And that works, but only in very controlled scenarios. Because in the real world, information rarely lives inside just one document. Think about enterprise systems. Audit reports are stored separately, policies live in different PDFs, risk guidelines are in another file, and compliance rule exists somewhere else entirely. Now, imagine asking a question like, does the audit report violate the policy guidelines? A basic rack system cannot answer this properly because it only knows how to look inside one document at a time. And this is where things get really interesting. In this video, we are taking rack to the next level. We're building a system where multiple documents are embedded together. A single question can pull context from different sources, and the model can reason across documents to produce a combined, grounded answer. Even more importantly, the answer will not be a black box. We'll make sure that the system clearly shows which document the information came from, which page it was extracted from, and how multiple sources contributed to the final response. And this is the foundation of enterprise-grade RAG systems, the kind used in legal analysis, compliance tools, research assistants, and internal knowledge copilots. So in this episode, you're not just learning another feature. You're learning how to move from toy RAG demos to real-world multi-document intelligence systems. So without any delay, let's get started. So for the implementation part, I have these two PDFs here. The first is ca.pdf, which contains node from computer architecture, and then the other is dl.pdf, which contains node for digital logic course. So I'm going to use these two PDFs to build this multi-document RAG here. And first of all, we'll start with import. So the first import is going to be from .env import load.env. Then I'm going to load the credential using this function here. I have some more imports to do. So from typing import list, and similarly from LangChain community dot document loaders, will import PyPDF loader. Again from LangChain dot text splitter, will import recursive character text splitter. From LangChain underscore Hugging Face, we're going to import Hugging Face embeddings. From LangChain Chroma, we will import Chroma. From LangChain core dot documents, we are going to import document. From LangChain core dot messages, we're going to import human message and a system message. Similarly, from LangChain core dot prompts, I'm going to import chat prompt template. Chat prompt template. From LangChain underscore grok, I'm going to import chat grok. And finally, I'm going to import OS to read the files inside this docs folder. Now, the first thing that I'm going to do is load multiple documents. Now, to do this, I'm going to mention the doc folder. So my doc folder is going to be the docs folder that I have created here, which contains two files. Now to load all the documents inside this doc folder, I'm going to create an empty list of document. For now, it is going to stay empty. Then I'll implement a loop. So for file in os.list directory, from inside the doc folder, I am going to check if my file, if file dot ends with dot pdf, then I'm going to do loader equal to pypdf loader dot, or I can directly do this os.path.join doc folder and file. Then I'll do docs equals to loader.load. After this, I'm going to attach a document level metadata with this. So for this, I'm going to do for d in docs d dot metadata, and then I'll keep it inside the tag source document equals to file, and finally I'm going to add everything inside all document, and I'll do all documents dot extend and then put in docs. So finally, let me first print what I've done here. So loaded length of all documents pages from multiple documents. Now in step number 2, I'm going to split documents here. So for this, I'm going to create a splitter object using recursive character text splitter. Here I'm going to define the chunk size as 1000, and then a chunk overlap as 100. Now after this, let me define chunk equal to splitter dot split underscore documents, and then provide all documents inside this. And finally, I'm going to print how many chunks have been created. So total chunks created is equal to len chunks. Then after this, I'll go to step 3, where we'll create embeddings. So for embeddings, we'll use the same model that we've been doing for the past few videos. We'll use one from Hugging Face Embeddings, where the model name is going to be sentence transformers all mini LM L6 V2. Now, along with this, I'm going to create a vector store. So for the vector store, I'm going to use Chroma, as I've already told you. So let me create a vector store object. So this will be Chroma dot from documents, and here I'm going to pass in the documents as chunks that I've created earlier here. Along with this, I'll pass in the embedding as our embedding model that we've defined earlier, and along with this, let me pass in a collection name. So the collection name can be anything. I'll say multi-doc rag now. Then I'll create a retriever object using the vector store dot as underscore retriever. And then I'll pass in the search keyword arguments here. So search quirks will be, let me extract the top 3 result for this particular case, or we'll do top 4 results for now. Okay. Now we move on to defining our LLM. So this was step 4. Now we move on to step 5, where we define our LLM. So for our LLM, we're going to use Chat Grok model. We'll be using the same Llama model that we've been doing since quite some videos. So Llama 3.3 with 70 billion parameters and versatile model. For the prompt, I'm going to define a prompt object using chat prompt template. Chat prompt template dot from messages. And first of all, I'm going to include a system message. The content of the system message is going to be you are an expert assistant. Let me do a multi-line string in this particular case. Okay, so you are an expert assistant. Answer only using the provided context. If multiple documents are involved, clearly mention them, and if the answer is not present, just say you don't know. So this is going to be my first system message here. Then I'm going to add one more human message. So in the case of human message, I'm going to pass in the context. The context will come from the context placeholder,
and then the question will come from the question placeholder. So this will be my prompt for this particular video. Now what I can do is in step number 7, I can define my RAG function. So for RAG function, I'm going to declare a function, call it multi-document RAG. I'm going to pass in the query here as a string. Then basically, we will use our retriever to invoke this query. Now, whatever content we get from the retriever, we are going to concatenate all of them into one single string here. So here I'm going to do dot join, and inside this, first of all, I'm going to connect what else? So my document or the source document will be mentioned as source.metadata.get, and as I had earlier provided it as source underscore document. Then what else? Okay, we're also going to add the page number from where we have extracted that particular document. So metadata, or we'll leave the page number for now. We'll just keep it as it is here. So just the document part. Then what else? So let me also add page content here inside this. I can make it multi-line document again directly. Then I will do d.page underscore content, and then this will be for every documents in docs here. So this is going to be my context. After this, I'm going to invoke my prompt here. So prompt dot invoke, and then we said that we would provide these two values in case of prompt. So I'm going to pass in those two values here. So the first value is going to be, let me wrap it inside a curly bracket. So the first value is going to be context. The context is the context that we prepared here. Then along with this, I'll also pass a query or question. I think it's not a query, it's a question. So question will be passed as query that we've received in this particular function here. Now finally, I can invoke my LLM LLM.invoke using the prompt that I prepared here, and then I can return response.document. Sorry, it's content, not document. Content comma docs. This is the actual model response, while docs actually contains the source document metadata to help us understand where our result is being extracted from. Now, finally, we will run our RAG application. So to do that, let me write a print statement here. So we'll call it multi-document RAG. Also, I'll present type exit to quit. Now, let me define an infinite loop while true. So query is going to be something that is going to come from the user. So I'll ask the query from the user here. Now, if query dot lower equals to exit, then I'm going to break it out of this loop. Or else, if there is a genuine user question, then I'm going to pass the query in the multi-document RAG function, and then basically get answer as well as sources from there. So my query is going to go to multi-document RAG function right here, and then I will get the answer as well as the sources for my answer here. Now, what I can do is I can basically print the AI answer, and then AI answer is going to be answer that I've just retrieved. And then since that particular answer could come from multiple sources, so I can do for I, comma D in enumerate sources, sources sources, and I can directly print. So let me do a multi-line string again here, or we can also do a single line string. It's fine. I'm going to do I plus 1 and D dot metadata dot get, and then source underscore document. Okay, so this is all for the implementation part here. Now we can run our code directly by calling Python RAG for multi-document RAG, and then see, basically use the application and then check whether information from multiple documents are retrieved or not. Sorry, I made a mistake here. I should have run this multi-document rag.py file instead of this above file here. Anyway, so they've loaded 231 pages from multiple documents. I think this document contains 130 pages, and then the CA document contains 101 pages. So yeah, total of 231 pages. The total chunk created was 486, and then I have this particular loop running here. So the user query is asked. Let me ask a very simple question about when is this particular computer organization and architecture as well as the DL subject taught here, basically in which semester. So if the model can provide me that particular answer here, then I think our objective is almost complete. So let me ask, in which semesters are computer organization and architecture and digital logic taught? So okay, what is this? So according to the provided document, digital logic is taught in second year first sem, which is correct, while computer organization is taught in third year and first semester, which is also correct. So yeah, the model is able to extract information from multiple documents and then combine them and basically provide our final answer. You can try many more questions inside this according to the PDFs that you have. You can upload any kind of PDFs inside this and then basically use your multi-document RAG model. So that is all for the demonstration or implementation of this video. So with this, we've officially crossed an important milestone in our RAG journey. We're no longer working with a system that understands just one document in isolation. We built a retrieval pipeline that can pull relevant information from multiple documents, combine that context intelligently, and generate answers that are grounded, explainable, and traceable. And this is exactly how real-world AI systems operate. In enterprise environments, questions almost always span between multiple reports, different policy documents, historical records, and evolving guidelines. And your RAG system must be capable of reasoning across document, not just inside one file. What you built in this video is the backbone of that capability. If you've made it this far, you've just completed a full end-to-end journey through Retrieval Augmented Generation. Congratulations to you. In this single video, we started from the very foundations: document loaders, text splitting, embeddings, vector stores, and retrievers, and then gradually assembled a complete basic RAG pipeline. From there, we went deeper. We looked at explainable RAG, where every answer is backed by sources. We built conversational RAG, adding memory so that the system can understand context across multiple turns. And finally, we explored multi-turn document retrievals, showing how RAG scales beyond a single data source. At this point, you should have a clear mental model of how RAG actually works internally. Not just what to code, but why each component exists and how they connect together. And this is exactly the foundation you need before moving into more advanced agent-based and production-grade systems. In the upcoming videos in this channel, we'll take these ideas further, optimizing retrieval, handling complex user queries, and building more autonomous intelligent pipelines. If this video helped you truly understand RAG, make sure to subscribe to the channel because the upcoming episodes in this channel builds directly on what you learned here. And if you found value in this deep dive, a like really helps the channel reach more learners like you. Thanks for watching. Thanks for staying till the end, and I'll see you in the next episode.